Are we the first civilization the universe has ever created? In the quiet of night, humanity looks upward. Billions of stars scattered across the darkness, each a sun, many with worlds of their own. We stand on our pale blue dot, gazing outward, wondering, are we alone? The question echoes through observatories and living rooms alike, through the thoughts of scientists peering through telescopes and children lying in fields looking up at the stars. Our radio signals have been traveling outward for over a century now, reaching farther and farther into the cosmos. Yet, in return, we hear nothing but cosmic whispers, static, background radiation, the afterglow of creation itself, but no voices, no messages, no evidence that anyone else has ever looked up at their own stars and wondered, as we do. The silence is profound. Each year, our instruments grow more sensitive, our search more comprehensive. We scan thousands of nearby stars across multiple frequencies. We analyze the atmospheres of distant planets for signs of technology. We search for megastructures, for laser pulses, for any hint of artificial origin among the natural processes of the universe. And still, we find nothing that cannot be explained by physics and chemistry alone. This cosmic silence stands in stark contrast to the abundance of potentially habitable worlds we now know exist. Astronomers have discovered thousands of planets orbiting other stars, many similar in size and orbit to our Earth. The building blocks of life, carbon and water, and energy appear common throughout the galaxy. The universe has existed for billions of years before our sun formed, providing ample time for life and intelligence to evolve elsewhere. Yet no clear evidence of other technological civilizations has been found. Perhaps the universe is teeming with life, with civilizations that rose and fell before our ancestors learned to make fire. Perhaps intelligent beings across countless galaxies are asking the same questions we are. Or perhaps, in all the vastness of space and time, we are the first to evolve, to build, to question, to reach outward. This possibility, that we might be among the earliest technological civilizations in the cosmos, challenges our intuition. We are accustomed to thinking of ourselves as latecomers to an ancient universe, as newcomers in a possibly crowded galaxy. The idea that we might be pioneers rather than joiners, teachers rather than students, ancestors rather than descendants in the cosmic story feels both exhilarating and terrifying. The cosmos is 13.8 billion years old. Our species, Homo sapiens, has existed for barely 300,000 years. We have been sending detectable signals to space for just over a century. In cosmic terms, we have only just awakened. Are we truly alone? Or are we simply the first to rise from the primordial waters, the first to develop technology, the first to wonder if others exist? To contemplate these questions is to confront the immensity of time and space, to attempt to grasp scales that strain our comprehension. Our galaxy alone contains hundreds of billions of stars. The observable universe contains hundreds of billions of galaxies. The time since the Big Bang spans nearly 14 billion years. Against these vast numbers, our existence seems simultaneously miraculous and inevitable. Given enough stars, enough planets, enough time, perhaps life and intelligence were bound to emerge somewhere. But how common is that emergence? How often does the cosmic dice roll come up with consciousness? This is a profound question with profound implications. If we are alone, we carry a unique responsibility. If we are first, we may be the ancestors other civilizations will someday search for. And if others have come before us, where are they? Why is the universe so quiet? The answer may lie in the extraordinary sequence of events that led to our existence. The precise composition of our planet, the stability of our star, the formation of our moon, the emergence of life, the development of complexity, the evolution of intelligence, the rise of technology. Each step represents a filter that may reduce the number of worlds that progress to the next level. If any of these filters is sufficiently restrictive, technological civilizations might be vanishingly rare in time and space. As we ponder these questions, we must confront the possibility that intelligence like ours might be vanishingly rare, that consciousness might be the most precious thing in existence, that despite all the stars and all the worlds and all the time that has passed since the universe began, we might be the first civilization to ever look up and ask, are we alone? Our search for others is ultimately a search for context, for understanding our place in the cosmic story. Are we the culmination of a long progression of intelligence across the galaxy? Are we typical, one of many technological species currently navigating their own path through the challenges of knowledge and power? Or are we truly pioneers, early arrivals in a universe that is just beginning to wake up to consciousness and purpose? The implications of these different possibilities extend far beyond scientific curiosity. They shape how we might think about our responsibilities to the future, about the potential longevity of our civilization, about the paths that lie open before us as we develop technologies of increasing power. If we are among the first, we bear the responsibility of setting precedents that may influence countless future civilizations across spans of time we can barely comprehend. Tonight, we explore this possibility. We examine the evidence, the theories, the hopes, and the fears. We consider what it would mean if humanity truly stands alone as the first civilization the universe has ever created, and what responsibility that places upon our shoulders as we take our first tentative steps into the cosmic ocean. Our journey will take us from the emergence of life on Earth to the vast scales of cosmic evolution. We will explore the great filters that might make technological civilizations rare, the search for signals from other worlds, and the meaning of potentially being first. We will look to the stars not just with our instruments, but with our imaginations, contemplating futures in which humanity either discovers we are part of a galactic community or confirms that we are indeed among the inaugural generation of cosmic intelligence. In either case, the night sky will never look quite the same again. Each point of light becomes not just a distant sun, but a question, a possibility, a potential cradle for consciousness, like and unlike our own. The darkness between the stars becomes not empty void, but opportunity, the canvas upon which the future story of intelligence in the cosmos has only just begun to be written. Our story begins in the grasslands of Africa, where our earliest ancestors stood upright and gazed across the savanna. The human journey started roughly 300,000 years ago, when Homo sapiens first emerged. For most of that time, we were hunters and gatherers, moving with the seasons, following herds, collecting what the land offered. We were few in number, perhaps never more than 1 million souls across the entire planet. Our tools were simple. Our knowledge passed through generations by spoken word alone. Imagine those early days. Small bands of humans huddled around fires as night fell, sharing stories, planning hunts, teaching children the ways of survival. Their world was immediate and intimate. They knew every plant, every animal track, every weather pattern in their territory. The night sky above was not merely beautiful, but functional, a map and calendar written in stars. They lived in a cycle of seasons that had continued unbroken for thousands upon thousands of years. These early humans possessed the same brains we have today, the same capacity for language, art, music, and abstract thought. Yet their lives were fundamentally different from our own. They created the first artworks, painting animals on cave walls with surprising skill and sensitivity. They crafted jewelry from shells and beads. They buried their dead with care, and perhaps with belief in something beyond the visible world. They were us, yet not us, standing at the beginning of the long road to civilization. The sophistication of these early ancestors is increasingly apparent to archaeologists. The cave paintings at Chauvet in France, created some 32,000 years ago, reveal not crude attempts at representation, but masterful understanding of anatomy, movement, and perspective. The flutes carved from bird bones and mammoth ivory found in Germany, dating back 40,000 years, were precisely tuned to musical scales we still recognize today. The beads, pendants, and figurines discovered across Europe, Asia, and Africa suggest complex symbolic thinking and aesthetic sensibility. These early humans were not just surviving but creating culture, developing shared meanings and values that bound their communities together. They traded materials over surprisingly vast distances, with shells from coastal regions found hundreds of miles inland, obsidian tools discovered far from volcanic sources. These exchange networks suggest social connections extending beyond immediate family groups, the earliest threads in what would become the complex web of human civilization. Their knowledge of plants and animals was encyclopedic, built through careful observation over countless generations. They understood which plants could heal, which could harm, which could nourish. They knew the migration patterns of animals, the subtle signs of changing seasons, the warning signals of approaching storms. This intimate knowledge of their environment allowed them to thrive in landscapes that would seem harsh and unforgiving to most modern humans. Then, around 12,000 years ago, something remarkable happened. In multiple places across the world, humans began to cultivate plants and domesticate animals. The agricultural revolution had begun. No longer did we need to wander. We could stay in one place, build permanent settlements, store food for lean times. Population grew. Specialization became possible. Some could farm, while others crafted tools, built structures, or contemplated the stars. This transition was not rapid or easy. Early farming was backbreaking work, less reliable than hunting and gathering in many ways. Archaeological evidence suggests that the first farmers were often less healthy than their nomadic counterparts, suffering from new diseases, dietary deficiencies, and the vulnerabilities of a fixed location. Yet the potential for growth was enormous. A plot of land that might support one hunter-gatherer could feed multiple farmers, albeit with more labor. Why did humans make this difficult transition? Perhaps it was driven by climate change at the end of the last ice age. Perhaps by population pressure in certain regions. Perhaps by the discovery that certain wild grains could be planted and harvested year after year. Whatever the trigger, once begun, agriculture created a new relationship between humans and their environment. We were no longer just inhabitants of the natural world, but shapers of it. The earliest farming communities were experiments in a new way of life. At sites like Çatalhöyük in modern Turkey, thousands of people lived in clustered mud brick houses, so tightly packed that residents entered through roof openings. They grew wheat and barley in nearby fields, raised sheep and goats, and maintained elements of their hunting and gathering past. Their homes were adorned with elaborate murals, their dead buried beneath the floors with grave goods suggesting complex beliefs about an afterlife. These communities were not yet cities as we would understand them, but they were no longer the small mobile bands of the hunter-gatherer era. They represented something new in human history, a different way of organizing society and relating to the landscape. They were the first step toward the urban centers that would eventually emerge across the globe. The domestication of plants and animals was itself a remarkable achievement. Through careful selection over many generations, humans transformed wild species into forms better suited to human needs. Wild teosinte, with its tiny, hard seeds, became the productive, easily harvested maize we know today. Wild aurochs became docile cattle. Wild wolves became loyal dogs. This process of domestication was not a sudden invention, but a gradual co-evolution, a dance between human needs and plant and animal genetics that continues to this day. From these first settlements emerged the earliest cities: Uruk and Eridu in Mesopotamia, Caral in Peru, Mohenjo-Daro in the Indus Valley. These concentrations of humanity enabled new forms of cooperation and competition. Writing developed, allowing knowledge to accumulate across generations without being lost. Mathematics, astronomy, philosophy, and art flourished. Civilizations rose and fell, each building upon the achievements and lessons of those that came before. The earliest cities were marvels of innovation. Irrigation systems channeled water to fields and homes. Walls protected against raids from those who still lived as nomads. Social hierarchies emerged, with rulers, priests, merchants, artisans, and farmers all playing distinct roles. For the first time in human history, a person might spend their entire life without needing to hunt or gather food. Craft specialization allowed for unprecedented refinement of tools and techniques. Artisans could spend decades perfecting a single skill, be it metalworking, weaving, or architecture. These complex societies required new forms of organization. Record-keeping began as simple tallies of goods, but evolved into true writing systems. Laws were codified, establishing the first formal rules for human behavior beyond tribal custom. Trade networks expanded, connecting distant regions and cultures. Ideas, technologies, and beliefs flowed along these same routes, creating a web of human connection that spanned continents. The emergence of writing around 5,000 years ago marked a profound shift in human history. In Sumer, Egypt, the Indus Valley, and later China, systems of visual symbols evolved from simple pictograms representing objects to complex scripts capable of expressing abstract ideas and recording spoken language. Writing allowed thoughts to traverse time, knowledge to accumulate beyond the capacity of any single memory, agreements to be recorded and referenced long after they were made. With writing came literature, history, formal religious texts, mathematical notation, astronomical records, and administrative documents. The earliest known author, whose name has survived, Enheduanna, composed hymns and poetry in ancient Sumer nearly 4,300 years ago. Her works were copied and recopied for centuries, an early example of how writing could preserve a single voice long after its physical form had perished. Education became increasingly formalized as writing and other specialized knowledge required systematic training. Schools emerged where scribes, priests, and administrators were taught the skills needed to maintain increasingly complex societies. These institutions created new social classes, new forms of authority based on knowledge rather than physical prowess, new hierarchies that would shape human societies for millennia to come. Consider the pace of this development. For roughly 290,000 years, human technology changed remarkably little. The hand axe, the spear, the bow and arrow, the atlatl, simple shelters, small bands of hunter-gatherers. Then in just the last 10,000 years, we went from the first permanent settlements to cities of millions. From the first crude writing to vast libraries of knowledge, from the first bronze tools to spacecraft that touch the stars. The development of metallurgy marks another crucial transition. First copper, then bronze, then iron. Each new material expanded what humans could build, farm, and fight with. Plows cut deeper into soil. Weapons became more lethal. Tools became more durable. The control of metal resources became a source of power and wealth, shaping the rise and fall of kingdoms and empires. The knowledge required to work these metals was not trivial. Copper ores must be identified, mined, crushed, smelted at specific temperatures, and cast or hammered into useful forms. Bronze, an alloy of copper and tin, requires bringing together metals often found in completely different regions, suggesting extensive trade networks and metallurgical experimentation. Iron is even more demanding, requiring much higher temperatures and complex techniques to remove impurities and incorporate carbon to create useful tools. These metallurgical innovations were not merely technical achievements, but transformative technologies that restructured societies. Control of metal deposits and trade routes became sources of wealth and power. Specialized classes of miners, smelters, and smiths emerged. Military technologies evolved rapidly, changing patterns of conflict and conquest. Agricultural productivity increased with metal tools, supporting larger populations and more complex social organizations. The invention of the wheel, around 5,500 years ago, revolutionized transportation. Combined with the domestication of horses and other draft animals, it allowed goods and people to move faster and farther than ever before. Roads connected cities and regions. Messages could travel hundreds of miles in days rather than weeks. These transportation networks facilitated not just the movement of goods, but the spread of ideas, technologies, religions, and artistic styles. Innovations could travel far from their points of origin, being adopted and adapted by diverse cultures. Writing systems spread along trade routes. Religious concepts migrated across linguistic and cultural boundaries. Architectural techniques and artistic motifs were borrowed and transformed as they moved from region to region. The ancient world was far more interconnected than we often imagine. Archaeological evidence reveals surprising connections. Chinese silk found in ancient Egyptian tombs, African ivory in Mesopotamian palaces, Baltic amber in Mediterranean jewelry, Indian cotton in Nubian graves. These material exchanges were accompanied by less tangible but equally important exchanges of knowledge, beliefs, stories, and technologies that created a complex web of cultural diffusion across the ancient world. And the greatest acceleration has come in just the last few centuries: industrial revolution, electricity, flight, computers, the internet, space exploration. In cosmic terms, this is the blink of an eye, a heartbeat, the smallest fraction of the smallest moment. Starting around 250 years ago, human civilization transformed at a pace unprecedented in history. The harnessing of fossil fuels, beginning with coal, unlocked energy stores that had accumulated over millions of years. Steam engines drove factories, trains, and ships. Cities swelled as rural dwellers migrated to industrial centers. The production of goods, once the work of individual artisans, became mechanized and standardized. The scale of this transformation is difficult to comprehend. For most of human history, the primary source of energy was human and animal muscle, supplemented by wind and water power. The energy captured in a piece of coal or a barrel of oil represents the solar energy accumulated by ancient plants over thousands of years, suddenly released for human use. This vast increase in available energy allowed for activities that would have seemed miraculous to earlier generations. Mountains could be moved, tunnels could be dug through solid rock, materials could be transformed at industrial scales. This unprecedented access to energy changed not just what humans could do, but how they lived and how they understood their relationship to the natural world. Time became measured with mechanical precision. Work moved from fields and home workshops to factories with their rhythms dictated by machines rather than seasons or natural light. Populations shifted from rural to urban settings, from agricultural to industrial, and eventually service occupations. The human experience itself was transformed in ways both liberating and alienating. Electricity changed everything again. Nights were no longer ruled by darkness. Communication became nearly instantaneous with the telegraph and telephone. Radio and later television created shared cultural experiences across vast distances. The rhythm of human life, once tuned to the rising and setting of the sun, became increasingly artificial and precisely measured. The development of electrical technologies represents another quantum leap in human capability. Electricity is not just another energy source, but a fundamentally different kind of force, one that can be transmitted instantly across vast distances, that can power devices of extraordinary precision and sensitivity, that can carry information as well as power. The ability to generate, transmit, and utilize electricity opened possibilities that earlier generations could scarcely have imagined. The electrical grid, connecting power plants to homes and businesses across entire continents, represents one of the largest and most complex machines ever built. This vast network, largely invisible in daily life, underlies almost every aspect of modern civilization. Without it, contemporary urban life would be impossible. Modern communications would collapse, industrial production would cease, and much of our accumulated knowledge would become inaccessible. Flight shrunk the world even further. Journeys that once took months could be completed in hours. The photographic view of Earth from space showed us, for the first time, our planet as a single, unified sphere, with no visible borders between nations. Computers and the internet created a new realm of human activity, a virtual world where information flows freely across the globe. The conquest of the air represents another transformation in the human relationship to the physical world. For all of prior history, humans were bound to the surface of the earth, limited in their movements by geography and the constraints of land and sea travel. Flight liberated us from these constraints, allowing movement that followed the most direct path rather than the contours of the landscape. It expanded our perspective, giving us a literal overview of our environment that revealed patterns and connections invisible from ground level. The development of computing technology marks yet another inflection point. Computers are not merely faster calculating machines, but devices capable of manipulating symbols, processing information, storing and retrieving data, and eventually connecting to form global networks. They extend not just our physical capabilities, as earlier technologies did, but our cognitive capabilities, allowing us to solve problems of complexity far beyond the capacity of the unaided human mind. The internet represents perhaps the most profound transformation since the development of agriculture or writing. It connects billions of humans in a single network, allowing near instantaneous communication and collaboration across the globe. It makes the accumulated knowledge of humanity available to anyone with a connection. It creates new forms of community, new modes of artistic expression, new economic relationships, new political movements. It is simultaneously a technology, a social space, an economic platform, and a global commons. What made this possible? What combination of factors allowed intelligence like ours to evolve, and then civilization to develop? The story is one of fortunate coincidences and evolutionary pressures that might be exceedingly rare in the universe. It began with our planet itself. Earth formed about 4.5 billion years ago, a sphere of rock at just the right distance from our star, not too close, not too far. What astronomers call the habitable zone. Liquid water could exist on the surface, neither constantly frozen nor boiled away. Our planet developed a magnetic field that shields us from harmful solar radiation. It has a large moon that stabilizes its axial tilt, preventing wild climate swings. It has plate tectonics that recycle carbon and other elements crucial for life. Without any one of these features, life as we know it might never have emerged. A planet slightly closer to its star might experience runaway greenhouse effects, becoming a scorched wasteland like Venus. One slightly farther might freeze solid. Without a magnetic field, solar radiation would strip away the atmosphere and bombard the surface with deadly particles. Without the stabilizing influence of our unusually large moon, Earth's axial tilt might vary wildly, causing extreme climate shifts that would make complex life difficult or impossible. Without plate tectonics, carbon might remain locked away, never recycling through the atmosphere to support photosynthesis. The precise balance of these planetary characteristics may be exceedingly rare. Most planets in our own solar system lack one or more of these crucial features. Venus is too hot, with no magnetic field and a toxic atmosphere. Mars is too cold, with a weak magnetic field and thin atmosphere. The gas giants have no solid surface where life like ours could emerge. Even among the thousands of exoplanets discovered so far, few appear to combine all the characteristics that have made Earth so hospitable to complex life. Our Sun, too, possesses unusual characteristics that may have facilitated the emergence of intelligence. It is remarkably stable, lacking the violent flares common to smaller stars. It produces energy across the spectrum needed for photosynthesis. It will maintain its current output for billions of years, providing the long-term stability that complex life requires to evolve. Many stars burn too hot, too cool, too erratically, or too briefly to support the gradual development of intelligence. Life appeared relatively early in Earth's history, perhaps as soon as 4 billion years ago. But for most of that vast span of time, life remained simple, single-celled organisms. For nearly 2 billion years, nothing more complex evolved. Then came the first multicellular life, animals, plants, a slow, gradual diversification of forms and functions. This long period of simple life suggests that while basic life might emerge relatively easily given the right conditions, the jump to complexity is far more difficult. It might require specific environmental triggers, rare genetic innovations, or simply vast amounts of time and chance. If this pattern holds true across the universe, planets might teem with microbial life, while remaining barren of anything more complex. The emergence of complex multicellular life on Earth may have required a series of unlikely events and innovations. The development of the eukaryotic cell, with its specialized internal compartments, appears to have happened only once, when one type of primitive cell engulfed another, eventually leading to a symbiotic relationship. This endosymbiosis event created the mitochondria that power all complex cells today. Without this singular event, life might have remained perpetually simple. The evolution of sexual reproduction represents another crucial innovation, allowing for genetic recombination and accelerated adaptation to changing conditions. The development of specialized cells and tissues, of bodies with distinct organs and systems, required complex genetic regulation and cell-to-cell communication systems. Each of these innovations may represent a significant evolutionary hurdle that few planets with simple life managed to overcome. Oxygen accumulated in our atmosphere, allowing for more energy-intensive life forms. The evolution of sexuality increased genetic diversity, speeding adaptation. Mass extinctions cleared ecological niches, allowing new forms to flourish, each step building on what came before in an unbroken chain of inheritance, stretching back to the first self-replicating molecules. The role of extinction events in the evolution of complex life presents a fascinating paradox. Catastrophes that nearly ended all life on Earth, like the Permian extinction that killed 95% of marine species and 70% of terrestrial vertebrates, created evolutionary opportunities for the survivors. The death of the dinosaurs allowed mammals, previously small and nocturnal, to expand into new niches and eventually evolve forms as diverse as bats, whales, elephants, and humans. Destruction paradoxically enabled innovation, clearing the evolutionary stage for new experiments in form and function. Yet extinction events that are too frequent or too severe might prevent complex life from ever developing. A planet bombarded too often by asteroids, racked by too many supervolcanic eruptions, or sterilized by intense radiation from nearby supernovae might reset the evolutionary clock repeatedly, never allowing the accumulation of complexity that eventually led to intelligence. Earth may represent a delicate balance, experiencing extinction events severe enough to drive evolutionary innovation, but not so catastrophic as to permanently prevent complexity. Our own lineage, the primates, evolved roughly 60 million years ago. The first hominids appeared around 7 million years ago. The genus Homo, to which we belong, emerged about 2.8 million years ago, and our own species, Homo sapiens, is just 300,000 years old. What made us different? What set us on the path to civilization when our cousins, the Neanderthals and Denisovans, remained hunter-gatherers? The answer lies in a perfect storm of adaptations. Bipedalism freed our hands for tool use. Changes in our throats and brains allowed for complex language. Our unusually long childhood gives time for learning and cultural transmission. Our social nature enabled cooperation on unprecedented scales. These adaptations did not evolve for the purpose of building civilization. They emerged through natural selection in response to specific environmental pressures. Bipedalism likely evolved as an adaptation to life in mixed woodland and savanna environments. Larger brains evolved as our ancestors, engaged in increasingly complex social interactions and tool use. Language may have emerged from systems of communication about food sources, predators, and social relationships. The human trajectory was not inevitable or predetermined. It depended on specific environmental pressures that might be rare elsewhere. Our ancestors evolved in an environment undergoing significant climate fluctuation, with mosaic landscapes containing multiple types of habitat in close proximity. This variability may have selected for behavioral flexibility and innovation. A more stable environment might have favored specialized adaptations rather than the generalist approach that characterizes human evolution. Our evolutionary pathway also depended on specific contingent events. If not for the asteroid impact that eliminated the dinosaurs, mammals might never have had the opportunity to diversify into the forms that eventually included primates. If not for the specific pattern of continental drift that created the East African Rift Valley, with its unique combination of woodlands and savannas, bipedalism might never have been advantageous. If not for specific cultural innovations like controlled use of fire, cooking, and cooperative hunting, our ancestors might never have developed the larger brains and social structures that characterize modern humans. Each of these adaptations built upon the others in a feedback loop. Bipedalism allowed for tool use, which selected for better hand control and larger brains. Larger brains allowed for more complex social structures and eventually language. Language allowed for better coordination and knowledge transmission, further selecting for cognitive abilities. At each step, the path to humanity could have taken a different turn. Intelligence like ours was not inevitable, but contingent on countless specific circumstances. Perhaps most importantly, we developed what anthropologists call behavioral modernity, abstract thinking, symbolic art, long-term planning, complex social structures. This cognitive revolution, occurring roughly 70,000 years ago, set us on a trajectory unlike any species before us. The capacity for symbolic thinking, for assigning meaning to marks, sounds, gestures, and objects, may be the most crucial adaptation for the eventual development of civilization. Symbols allow for the transmission of complex ideas across time and space. They enable the creation of shared realities beyond immediate physical experience. They make possible the languages, writing systems, mathematical notations, artistic traditions, religious beliefs, and scientific theories that form the foundation of human civilization. This symbolic capacity may have emerged from a complex interplay of biological and cultural factors. Genetic changes affecting brain structure and function provided the neurological substrate for abstract thought. Cultural innovations like rituals, art, and storytelling created contexts where symbolic thinking was advantageous. Once established, symbolism became self-reinforcing, as each generation was born into a world already filled with meanings beyond the immediately physical. But even with these adaptations, civilization was not inevitable. Geography played a crucial role. Locations with predictable seasonal floods made agriculture easier to develop. The availability of domesticable plants and animals varied dramatically across continents. Some regions had wheat, rice, or corn. Others had potatoes or taro. Some had cows, pigs, horses, or chickens. Others had few or no animals suitable for domestication. The distribution of these resources was not random, but shaped by geological and evolutionary history. The east-west orientation of Eurasia allowed crops and animals domesticated in one region to spread to others with similar climates. The north-south orientation of the Americas, with its dramatic climate shifts across latitudes, made such spread more difficult. Some continents, like Australia, had very few domesticable species at all. These accidents of geography influenced which human populations first developed agriculture and, consequently, civilization. The uneven distribution of resources extended beyond domesticable species. Some regions possessed abundant deposits of copper, tin, and iron, facilitating the development of metallurgy. Others had stone suitable for building or carving. Still, others had materials like obsidian or jade that could be traded over long distances for their practical or aesthetic value. The location of rivers, natural harbors, mountain passes, and fertile valleys further shaped which societies could trade, expand, or defend themselves effectively. Climate also played a crucial role. The end of the last ice age created conditions favorable for agriculture in certain regions. Later, climate shifts led to the collapse of some early civilizations and the rise of others. The medieval warm period facilitated Norse exploration of the North Atlantic. The Little Ice Age contributed to famines and political instability across Europe and Asia. These climatic influences continue today, with global warming creating new opportunities and challenges for human societies worldwide. Access to metal ores, building materials, and trade routes influenced which civilizations flourished and which faltered. Climate shifts opened and closed opportunities throughout history. The interconnectedness of Eurasian societies allowed innovations to spread across vast distances, while more isolated regions had to reinvent technologies independently. When we look at this sequence of events, this cascade of fortunate circumstances and adaptations, we begin to appreciate how contingent our civilization truly is. Small changes in Earth's history might have prevented intelligence like ours from ever evolving. Different geographical distributions of resources might have prevented agriculture from developing. Without agriculture, cities would not have formed. Without cities, specialized knowledge could not accumulate. Without that accumulation, science and technology as we know them would never have developed. This contingency does not make our existence meaningless, but rather highlights its precious improbability. The particular form of intelligence and civilization that has emerged on Earth is the product of countless specific events and circumstances, stretching back to the formation of our solar system and beyond. The path from cosmic dust to conscious beings capable of contemplating their own origins was neither direct nor inevitable. It wound through innumerable branching possibilities, each dependent on specific conditions that might be rare elsewhere in the universe. The timeline of humanity is but the tiniest sliver of cosmic history. The universe has existed for 13.8 billion years, our species for 300,000 years, our civilization for perhaps 10,000, our industrial technology for mere centuries, our ability to send detectable signals to space for just over 100 years. We are cosmic newcomers, having just arrived at the doorstep of the universe. We have barely begun to explore our own solar system, let alone the hundreds of billions of stars in our galaxy, or the hundreds of billions of galaxies beyond. The question then becomes, are we truly the first? Or simply the latest in a long line of cosmic civilizations? If we are the first, it would be because the path to intelligence and civilization is extraordinarily difficult, filled with evolutionary bottlenecks and planetary conditions that may be exceedingly rare. If we are not the first, then where are the others? Have they risen and fallen already, leaving no trace we can detect? Or are they out there still, separated from us by the vast gulfs of space and time? These questions bring us to the age of the universe itself, and whether there has been enough time for other civilizations to evolve before our own. For if the universe has existed for nearly 14 billion years, and humanity needed just a few 100,000 to develop technology, surely others could have done the same long before us. Unless something prevents it, unless we truly are among the first sparks of consciousness in an otherwise dark cosmic ocean. In the vastness of space and the immensity of time, our existence seems simultaneously miraculous and inevitable. The particular form of life and intelligence that has emerged on Earth may be vanishingly rare, the product of a specific planetary history that few other worlds have shared. Yet the basic ingredients, the physical laws, the chemical elements, the energy sources necessary for life, exist throughout the cosmos. Whether they have combined elsewhere to produce beings capable of asking the same questions we now pose, remains one of the greatest mysteries we face as we look outward to the stars and inward to our own origins. To truly grasp the question of whether we are the first civilization, we must understand the age and scale of the cosmos in which we exist. The universe stretches back 13.8 billion years to an event we call the Big Bang. Not an explosion in space, but an expansion of space itself. All matter, energy, and even time as we understand it came into being in that moment. The very fabric of reality began to unfold, setting the stage for everything that would follow. In the first tiny fractions of a second, the fundamental forces of nature separated from one another: gravity, electromagnetism, the strong and weak nuclear forces. The most basic particles formed and annihilated each other in a seething plasma hotter than any star. For nearly 400,000 years, the universe was opaque, filled with energy so intense that light could not travel freely. Then came the first major transition. The universe cooled enough for electrons to combine with protons, forming the first atoms, mostly hydrogen with some helium and trace amounts of lithium. Light could now travel unimpeded across the cosmos. This ancient light still bathes us today, detectable as the cosmic microwave background radiation, a faint glow coming from all directions in space, the echo of creation itself. For millions of years after this clearing, the universe was a vast, dark cloud of primordial gas. No stars yet shone, no planets existed. Just vast, slowly cooling clouds of hydrogen and helium, gradually being pulled together by gravity into ever denser structures. These first gravitational wells became the seeds of the first galaxies, the cosmic structures that would become the birthplaces of stars. Around 100 million years after the Big Bang, the first stars ignited. These were not stars like our Sun. They were giants, containing perhaps 100 or even 1,000 times more mass. They burned hot and bright and brief, their immense gravity crushing their cores until nuclear fusion began. These stellar furnaces forged the first heavy elements, carbon and oxygen and nitrogen, the building blocks that would one day make life possible. These first stars lived fast and died young. After only a few million years, they exhausted their fuel and died in spectacular explosions called supernovae, scattering their newly forged elements into space. Some collapsed into the first black holes, gravity wells so deep that not even light could escape them. These stellar remnants, both the scattered elements and the black holes, became the seeds for the next generation of cosmic structures. By 500 million years after the Big Bang, the first galaxies had formed, collections of stars bound together by gravity, spinning in vast cosmic whirlpools. Within these galaxies, new stars formed from the enriched gas clouds left by their predecessors. These second and third generation stars contained more heavy elements. Around some of them, disks of dust and gas began to form, the precursors to planetary systems. Our own Milky Way galaxy took shape during this era, a spiral galaxy containing hundreds of billions of stars, It formed through the merger of smaller galaxies and the steady accretion of gas from the intergalactic medium. At its center grew a supermassive black hole, millions of times more massive than our Sun, around which the entire galactic disk would eventually rotate. But the universe was still young, still evolving. About 4 billion years after the Big Bang, a mysterious force began to accelerate the expansion of the universe. Astronomers call it dark energy, though its true nature remains one of the biggest mysteries in physics. Because of dark energy, galaxies began moving away from each other at an accelerating rate, stretching the cosmic web of structure into the vast network we observe today. Throughout this time, stars continued to form and die, each generation enriching the cosmos with more heavy elements: carbon, oxygen, silicon, iron. Elements forged only in the cores of stars, or in their explosive deaths. Elements essential for rocky planets, and, eventually, for life. 9 billion years after the Big Bang, in an unremarkable spiral arm of an unremarkable galaxy, a cloud of star-forming gas began to collapse. This cloud, enriched by the deaths of earlier stars, contained not just hydrogen and helium, but significant amounts of heavier elements. As it collapsed, it formed our Sun at its center, with a swirling disk of dust and gas around it from which the planets would form. Earth and the other planets of our solar system coalesced from this disk about 4.5 billion years ago. Countless collisions between planetesimals, some as large as Mars, shaped the early Earth. One such impact, with a Mars-sized body astronomers call Theia, gave birth to our Moon. The early Earth was a hellscape, molten and bombarded constantly by asteroids and comets, irradiated by a young, unstable sun. Gradually, Earth cooled. Water delivered by comets and outgassed from its interior formed oceans. A protective atmosphere developed. By 4 billion years ago, conditions had stabilized enough for the first simple life forms to emerge. For the next 3.6 billion years, life on Earth evolved, growing more complex, more diverse, more adaptable, eventually giving rise to creatures capable of wondering about their place in the cosmos. When we consider this timeline, a profound realization emerges. The universe is old, far older than our planet, far, far older than our species. Stars lived and died before our Sun ever formed. Galaxies collided and merged before our solar system existed. The cosmos had already existed for 9 billion years before our planet formed. 9 billion years, during which stars and planets came and went, during which the ingredients for life were being forged and scattered across space. 9 billion years is an almost incomprehensible span of time. To put it in perspective, if the entire history of humanity, from the first stone tools to the present day, were compressed into a single year, 9 billion years would be more than 30,000 years. If our civilization were a day old, the universe would have existed for over 4,000 years before us. This vast age raises a crucial question in our search for cosmic companionship. If the universe has existed for so long, with so many stars and planets, why do we appear to be alone? This question becomes even more pressing when we consider that the universe might actually be at a relatively early stage in its habitable lifetime. Current cosmological models suggest that star formation in the universe will continue for trillions of years. Red dwarf stars, the most common type in the cosmos, can shine for up to 10 trillion years. Even after star formation eventually ceases, existing stars will continue to shine for trillions more years. The era of stars, the time when life as we know it could potentially exist, might last for 100 trillion years or more. If we place ourselves on this cosmic timeline, humanity does not appear at the end of a long, inevitable progression. Rather, we find ourselves very near the beginning of the habitable lifetime of the universe. If the habitable era of the universe will last 100 trillion years, and the universe is currently 13.8 billion years old, then we have arrived after just 0.014% of the potentially life-supporting history of the cosmos has elapsed. This realization has profound implications for our question. We are not latecomers to a universe nearing the end of its life-supporting phase. We are early risers, awakening near the beginning of a vast cosmic day. The stars that exist now represent just the first tiny fraction of all the stars that will ever form. The planets that exist now are just the first microscopic percentage of all the planets that will ever circle their stars. But if we are so early in the cosmic story, why do we not see evidence of others who awakened before us? Even a head start of a few million years, a cosmic eye blink, would give a civilization tremendous technological advantages over our own. A civilization just 1% older than ours might be unimaginably advanced from our perspective. One possibility is that we truly are among the very first technological civilizations to emerge in our galaxy, or even in the universe. This may seem unlikely given the vast number of stars and planets that have existed before us, but several factors could make this more plausible than it first appears. First, while the universe is old, the elements necessary for life as we know it, particularly carbon, oxygen, and other heavy elements, have been steadily increasing over cosmic history. The earliest stars contained almost none of these elements. Even by the time our Sun formed, the cosmic abundance of heavy elements was lower than it is today. If certain key elements are necessary for life, earlier eras of cosmic history might have been less conducive to its emergence. Second, the rate of dangerous cosmic events, such as supernovae, gamma-ray bursts, and active galactic nuclei has decreased over time. The early universe was a more violent place, with higher rates of star formation and death, more frequent galaxy mergers, and more active supermassive black holes. These events can sterilize large regions of space, potentially preventing the long-term stability needed for intelligence to evolve. Third, it may be that while simple life might emerge relatively easily given the right conditions, the path to intelligence and technology is extraordinarily rare and filled with evolutionary bottlenecks that few species successfully navigate. Perhaps we are not the first life in the universe, but we might be among the first intelligent, technological species. Fourth, the development of intelligence might require very specific planetary conditions that were less common in the past. Our intelligence evolved in response to specific environmental pressures and opportunities on Earth. If these conditions are rare, or take a long time to develop on most planets, intelligent life might be only now emerging across the cosmos. However, these explanations face a significant challenge. Even if intelligence and technology are extremely rare, the sheer number of stars and planets that have existed before us is so vast that it seems incredible that none developed civilizations before our own. The Milky Way alone contains approximately 100 billion stars. Astronomers now believe that most stars host planets, with perhaps 20% harboring planets in their habitable zones. Over the 9 billion years before Earth formed, countless habitable worlds must have existed. If even 1 in a million habitable planets developed intelligent life, and if even 1 in 1,000 of those developed technology, there would still be thousands of technological civilizations that preceded us in our galaxy alone. Where are they? Why do we see no evidence of their existence? This brings us to another possibility. Perhaps we are not the first, but civilizations tend to be either short-lived or limited in their ability to expand beyond their home planets or solar systems. Perhaps the very technologies that allow a species to become detectable across interstellar distances also create existential risks that few civilizations survive. Or perhaps there are insurmountable physical limitations to interstellar travel and communication that keep civilizations isolated and undetectable to one another. The age of the universe provides both the time necessary for many civilizations to have evolved before us and the vastness of space and time that might keep them hidden from our view. A civilization that rose and fell a billion years ago on the other side of our galaxy would likely leave no trace we could detect today. A civilization currently thriving around a star 1,000 light-years away might be using communication technologies we have not yet discovered, or might simply not be trying to make contact with potential neighbors. The old age of the universe also means that civilizations need not be contemporaneous to influence one another. A technological species that arose 1 billion years ago and seeded the galaxy with robotic probes before dying out might still have those probes active today. A civilization that collapsed millions of years ago might have left artifacts or altered environments that could eventually be discovered. We might be surrounded by the ghosts of ancient civilizations without realizing it. As we ponder these possibilities, we must also consider the limitations of our own perspective. Our search for other civilizations has been brief, spanning just a few decades of dedicated effort. We have thoroughly examined only a tiny fraction of even our own galaxy. Our technology for detecting potential technosignatures is still in its infancy. The absence of evidence is not necessarily evidence of absence, especially when our search has been so limited in scope and sensitivity. The age of the universe tells us that there has been ample time for other civilizations to emerge before our own. The question of whether we are the first must therefore address not just whether we are the first ever, but why we do not detect those who might have come before us. As we continue our exploration of cosmic civilization, we must consider not just the ingredients for life, but the path from chemistry to consciousness, from simple organisms to technological societies. For in that path may lie the answer to why, in a universe so ancient, we find ourselves alone, gazing out at the silent stars. What does it take for life to begin? What raw materials are necessary for those first crucial steps from chemistry to biology? For much of human history, life was thought to be a special phenomenon, unique to Earth, requiring some vital spark or divine intervention. But as our scientific understanding has deepened, we have discovered something remarkable. The basic ingredients for life, far from being rare or special, are among the most common substances in the universe. Begin with water, the solvent in which life as we know it operates. Every cell in every living thing on Earth contains water. It dissolves and transports nutrients, facilitates chemical reactions, and helps maintain temperature. For decades, astronomers believed liquid water might be vanishingly rare in the cosmos. But recent discoveries have revealed quite the opposite. Water, in the form of ice, exists throughout our solar system. On Mars, beneath its dusty surface. On Europa and Enceladus, moons of Jupiter and Saturn, where vast subsurface oceans lie hidden beneath icy crusts. In the rings of Saturn, on comets and asteroids, even in the clouds of interstellar space. Beyond our solar system, the evidence continues to mount. Water vapor has been detected in the atmospheres of exoplanets, planets orbiting other stars. The building blocks of water, hydrogen and oxygen, are among the most abundant elements in the universe. Hydrogen, the most common element of all, was formed in the Big Bang itself. Oxygen is forged in the hearts of stars and scattered across space when those stars die. Wherever these elements meet under the right conditions, water forms. Then there are the organic molecules, compounds containing carbon bonded with other elements. These are the alphabet from which the language of life is written. Proteins, DNA, cell membranes, all are made of organic molecules, and these too are far from unique to Earth. In the cold, dark clouds between stars, astronomers have detected complex organic molecules, methane, ethanol, formaldehyde, amino acids, the building blocks of proteins. In some clouds, there are molecules so complex that scientists have not yet been able to identify them precisely. These interstellar clouds are the nurseries where new stars and planets form. The organic compounds they contain become part of those new worlds from the very beginning. Within our own solar system, organic molecules are equally widespread. They have been found on Mars, in the atmosphere of Saturn's moon Titan, in the plumes erupting from Enceladus, and in countless comets and asteroids. The Rosetta mission to comet 67P Churyumov-Gerasimenko found 16 different organic compounds, including the amino acid glycine, a fundamental component of proteins. Carbonaceous chondrites, a type of meteorite, contain even more complex organic compounds. Some that have fallen to Earth harbor thousands of different organic molecules, including nucleobases, the key components of DNA and RNA. These meteorites are fragments of asteroids, remnants from the formation of our solar system, suggesting that the ingredients for life were present from the very beginning of Earth's history. The abundance of these building blocks challenges our understanding of how unique life might be in the cosmos. If the ingredients are everywhere, might the recipe have been followed elsewhere? To answer this, we must look deeper at the chemistry that bridges non-living matter and living organisms. At its most fundamental level, life is a set of chemical reactions that can reproduce themselves and evolve over time. The simplest known living organisms are single-celled bacteria and archaea, yet even these are incredibly complex, with thousands of genes and proteins working in concert. The gap between non-living chemistry and even the simplest cell seems vast. How was it first crossed on Earth? And could it have been crossed elsewhere? Scientists have proposed several scenarios for the origin of life on Earth, each with its own merits and challenges. One hypothesis centers on deep-sea hydrothermal vents, where hot, mineral-rich water flows from cracks in the ocean floor. These vents create chemical and thermal gradients that could have powered the first metabolic reactions. They provide a constant supply of energy and a diverse mix of compounds that could interact in complex ways. Another hypothesis focuses on shallow pools or shorelines, where cycles of wetting and drying could concentrate organic molecules and facilitate chemical reactions. Ultraviolet light from the sun could have provided energy for these reactions, while clay minerals might have served as templates for the organization of the first complex molecules. Other proposals look to the skies, suggesting that some of the crucial steps in life's origin might have occurred in space or on other celestial bodies, with the results delivered to Earth by comets or meteorites. The cold of interstellar space can actually facilitate certain types of chemical reactions, and the radiation present in space can drive the formation of complex molecules. Regardless of which scenario is correct for Earth, and perhaps multiple pathways contributed, the important realization is that the transition from chemistry to biology does not require any mystical or unique conditions. It requires energy, the right mix of elements, and time. These are all abundantly available throughout the cosmos. Consider energy sources. Stars bathe their planets in radiation across the electromagnetic spectrum. Geological activity, powered by the heat of radioactive decay or gravitational compression, can create chemical and thermal gradients. Tidal forces from nearby planets or moons can heat worlds through friction. Even the chemical energy stored in molecules delivered by comets and meteorites could power prebiotic reactions. These energy sources exist throughout the universe. Our Sun is just one of hundreds of billions of stars in our galaxy alone, and each of those stars is a potential source of energy for chemical evolution on its planets. Geological activity has been observed on numerous worlds in our solar system and is likely common on rocky planets around other stars. Tidal heating is known to warm several moons in our solar system and would occur in any system where celestial bodies orbit close to each other. What about the right mix of elements? As we have seen, the elements essential for life as we know it, hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur, often abbreviated as HCNOPS, are among the most common in the universe. Hydrogen and helium were formed in the Big Bang. Carbon, nitrogen, and oxygen are forged in the cores of stars through nuclear fusion and then scattered across space when those stars die. Heavier elements like phosphorus and sulfur are created in the violent explosions of supernovae, the deaths of the most massive stars. Each generation of stars enriches the cosmos with more of these elements. The universe has been producing and distributing the building blocks of life for billions of years. Our own solar system formed from a cloud of gas and dust, already enriched by previous stellar generations, giving us a planet with all the necessary ingredients in abundance. Time, the third requirement, is something the universe has in abundance. As we explored in the previous chapter, the cosmos has existed for nearly 14 billion years. Stars and planets have been forming for most of that time. Even if the transition from chemistry to biology is extraordinarily rare, requiring highly specific conditions and multiple chance events, the universe has had time for countless experiments on countless worlds. Given the widespread availability of the ingredients for life, the diverse energy sources that could power prebiotic chemistry, and the vast expanses of time available, it seems almost inevitable that life would have emerged somewhere beyond Earth. Yet this brings us back to our central question. If the ingredients for life are everywhere, and there has been time for life to evolve elsewhere, where is everybody? Why do we not see evidence of other technological civilizations? One possibility is that while the basic ingredients for life are common, the specific conditions needed for life to actually emerge are rare. Perhaps the transition from chemistry to biology requires a precise sequence of events that seldom occurs. Maybe certain key steps in the process are highly improbable, acting as filters that few worlds pass through. Another possibility is that life itself is common, but complex multicellular life is rare. On Earth, single-celled organisms emerged relatively quickly after the planet cooled enough to support life, perhaps within a few 100 million years. But complex multicellular life took much longer to appear, more than 3 billion years. If this pattern holds true elsewhere, many worlds might harbor microbial life, but nothing more complex. A third possibility is that while the ingredients for life, as we know it, are widespread, life elsewhere might be based on different chemistry altogether. Perhaps there are forms of life so different from our own that we would not recognize them, or that would not be detectable by our current search methods. To explore these possibilities further, let us consider the places in our own solar system where scientists believe life could potentially exist based on the presence of the necessary ingredients. Mars, our closest planetary neighbor, once had liquid water flowing on its surface. Ancient riverbeds, lake basins, and mineral deposits all testify to a warmer, wetter past. Though the surface is now cold and dry, liquid water may still exist beneath the surface. The Martian soil contains organic compounds, and the atmosphere, while thin, provides some protection from radiation. If life ever emerged on Mars, it might still exist today, in subsurface habitats. Europa, a moon of Jupiter, harbors a global ocean beneath its icy crust. This ocean contains more water than all of Earth's oceans combined. It is heated by tidal forces from Jupiter and potentially by hydrothermal vents on the sea floor. The necessary chemical elements are likely present, delivered by comets or produced by radiation-induced chemistry on the surface ice. Europa may have all the ingredients needed for life. Enceladus, a moon of Saturn, is similar to Europa, but with a crucial difference. Plumes of water vapor erupt from its south pole, allowing scientists to directly sample the composition of its subsurface ocean. These samples, analyzed by the Cassini spacecraft, contained organic compounds and molecular hydrogen, a potential energy source for microorganisms. Enceladus presents one of the most promising environments for life in our solar system. Titan, Saturn's largest moon, offers a very different potential habitat. With a thick atmosphere rich in nitrogen and methane, lakes and seas of liquid hydrocarbons on its surface, and a likely subsurface water ocean, Titan is a world of complex chemistry. While too cold for liquid water on its surface, it might host forms of life based on different biochemistry than our own, perhaps using liquid methane or ethane as a solvent instead of water. These worlds in our own solar system, each with its own combination of the ingredients for life, represent just a tiny sample of the potentially habitable environments in the universe. As we discover more exoplanets around other stars, we continue to find worlds that could harbor the conditions for life. The discovery of exoplanets has been one of the most significant astronomical breakthroughs of recent decades. Before 1992, we knew of no planets beyond our solar system. Now we have confirmed the existence of over 5,000, with thousands more candidates awaiting verification. These range from gas giants larger than Jupiter to rocky worlds smaller than Earth, orbiting stars of all types and ages. Most remarkably, we now know that planets are not rare accidents, but the common outcome of star formation. Nearly every star appears to host at least one planet. Many host entire systems of worlds, some resembling our solar system, others quite different. The diversity of these planetary systems is staggering, revealing configurations we never imagined based on our single example. Of particular interest are planets in the habitable zone of their stars, the region where temperatures might allow liquid water to exist on the surface. Depending on the type of star and the planet's atmosphere, this zone can be relatively wide or narrow, but throughout the galaxy, astronomers estimate there may be billions of planets in habitable zones. Billions of worlds where the temperature is right for liquid water, where organic chemistry could flourish, where life might have a chance to emerge. Beyond individual planets, there are other environments where the ingredients for life might come together. Rogue planets, worlds ejected from their star systems, might maintain subsurface oceans heated by radioactive decay. Brown dwarfs, objects too massive to be planets but too small to be stars, might host worlds in their own habitable zones. Even the spaces between stars contain vast clouds of gas and dust where complex chemistry occurs. The cosmic inventory of potentially life-supporting environments is far larger and more diverse than we imagined even a few decades ago. And nearly everywhere we look, we find the same basic ingredients, the universal building blocks from which life on Earth is constructed. This ubiquity of life's ingredients forces us to confront a profound possibility. Life, in some form, may be common in the universe. Microbial life, at least, might exist on countless worlds across the cosmos. Yet complex life, particularly intelligent technological life like our own, appears to be exceedingly rare. If it were common, surely we would have detected some sign of it by now. This disparity suggests that there may be additional filters or bottlenecks that life must pass through on the path from simple chemistry to intelligence and technology. While the ingredients for life are everywhere, the path from those ingredients to beings capable of wondering about their place in the cosmos may be strewn with obstacles that few lineages successfully navigate. To understand these potential obstacles, we must look more closely at how life on Earth progressed from simple, single-celled organisms to the complex, diverse biosphere we see today. For while the ingredients may be common, the recipe for intelligence may be far more specific and demanding. The history of life on Earth suggests that some transitions may be relatively easy, occurring whenever the right conditions are present. The emergence of simple cells, for instance, appears to have happened relatively quickly once Earth cooled enough to support them. Similarly, once the right cellular machinery evolved, simple multicellularity developed independently many times in different lineages. Other transitions, however, appear to have been rare, chance events that might easily never have occurred. The evolution of complex cells with specialized internal structures, known as eukaryotes, seems to have happened only once in Earth's history. The development of sexual reproduction, which dramatically increases genetic diversity, and the rate of evolution also appears to have been a singular event. Most significantly, the evolution of intelligence and technology like our own has occurred just once on Earth, despite billions of years of evolution and countless species. This suggests that intelligence, particularly the sort capable of developing civilization and technology, may be an extremely rare outcome even when life itself is present. If these patterns hold true across the cosmos, we might live in a universe teeming with simple life, but nearly devoid of technological civilizations. The ingredients for life may be everywhere, but the specific sequence of events leading to beings like ourselves might be vanishingly uncommon. Yet we must be cautious about generalizing from our single example. Life elsewhere might follow different evolutionary pathways, face different selective pressures, and develop different forms of intelligence than our own. The universe may be more creative and diverse than we can imagine, producing countless experiments in the chemistry of life across billions of worlds. As we continue our search for life beyond Earth, we must remain open to possibilities beyond our current understanding. The ingredients for life as we know it are indeed everywhere, scattered across the cosmos in abundance. What recipes the universe has followed with those ingredients, what strange and wonderful forms might have emerged, remains one of the greatest mysteries we face. A mystery that speaks directly to our question of whether we are truly the first civilization in the vast cosmic story. The gap between non-living matter and conscious intelligence is vast. To understand whether we might be the first civilization in the universe, we must examine this extraordinary transition. How does a collection of atoms, following only the laws of physics and chemistry, become a being capable of wondering about its own existence? This journey from simple molecules to minds like our own is perhaps the most remarkable story in the cosmos. The first critical step is abiogenesis, the emergence of life from non-life. On Earth, this process occurred sometime between 4.5 and 3.7 billion years ago. The exact details remain unknown, one of the greatest mysteries in science, but the broad outlines have come into focus through decades of research. In the primordial seas of early Earth, simple organic molecules accumulated. Some of these may have formed on Earth itself, created by energy sources like lightning, ultraviolet radiation, or hydrothermal vents acting on the primordial atmosphere and oceans. Others may have arrived from space, delivered by the constant rain of comets and meteorites that bombarded the young planet. These simple molecules, through countless chemical reactions over millions of years, gradually formed more complex structures. Fatty acids spontaneously arranged themselves into bubbles, the precursors to cell membranes. Amino acids linked together into short protein-like chains. Nucleotides, the building blocks of RNA and DNA, began to form simple genetic molecules. At some point, a critical threshold was crossed. A chemical system emerged that could reproduce itself and evolve. This was not yet a true cell, as we would recognize it today, but rather a self-sustaining network of chemical reactions, perhaps enclosed within a simple membrane. This system could make rough copies of itself, with variations. Those variations that enhance stability or replication efficiency would have become more common over time. Natural selection, the engine of evolution, had begun at the molecular level. From these humble beginnings, the first true cells eventually emerged. These were likely similar to modern prokaryotes, simple cells without internal compartments. They contained genetic material, either RNA or primitive DNA, that carried instructions for their construction. They were surrounded by membranes that separated their internal chemistry from the external environment. They had metabolisms that extracted energy from their surroundings to power their activities. These first cells were the ancestors of all life on Earth. Every organism alive today, from bacteria to blue whales, from mushrooms to maple trees, from amoebas to humans, can trace its lineage back to those original cells. The universal genetic code, shared by all living things with only minor variations, testifies to this common origin. For nearly 2 billion years, life on Earth remained at this simple, single-celled stage. Prokaryotic cells diversified into countless forms, adapting to every available habitat. They colonized the oceans, the shorelines, the mudflats. They learned to use different energy sources, from sunlight to chemical compounds. They developed various metabolic strategies, from aerobic respiration to fermentation to photosynthesis, but they remained relatively simple in their internal structure and organization. Then, around 2 billion years ago, a remarkable event occurred. Two different types of prokaryotic cells entered into a symbiotic relationship that became so intimate that they eventually merged into a single, more complex cell. One cell took up residence inside the other, eventually evolving into the mitochondria, the power plants of modern complex cells. This event gave rise to the eukaryotes, cells with specialized internal compartments and much larger genomes than their prokaryotic counterparts. This merger appears to have been a singular event in Earth's history. It happened only once, creating a new branch on the tree of life. The rarity of this occurrence suggests that it may be a significant bottleneck in the evolution of complex life. If this pattern holds true throughout the universe, many worlds might harbor prokaryotic life, but very few would have made the leap to eukaryotes. The emergence of eukaryotes set the stage for another major transition, the evolution of multicellularity. Single cells began to stick together, initially in simple colonies where each cell remained essentially independent. Gradually, these colonies became more integrated, with cells specializing in different functions and communicating with one another to coordinate their activities. Multicellularity has evolved independently multiple times in Earth's history, in different lineages of eukaryotes. This suggests that once the foundation of complex cells exists, the transition to simple multicellular life may be relatively straightforward. However, the development of complex multicellular organisms with specialized tissues and organs appears to have been much more rare, evolving independently perhaps only a dozen or so times. The fossil record reveals a long period of relatively simple multicellular life, followed by an explosion of diversity. The Ediacaran and Cambrian periods, roughly 600 million to 500 million years ago, saw the emergence of most of the major animal body plans that exist today. This burst of innovation established the foundation for the complex ecosystems that would follow. What drove this sudden diversification remains debated. One hypothesis suggests that the evolution of predation created an evolutionary arms race, with prey developing new defenses and predators developing new ways to overcome them. Another points to increases in atmospheric oxygen that made more energetically demanding lifestyles possible. A third suggests that genetic innovations, such as new developmental toolkits, opened up previously inaccessible evolutionary pathways. Whatever the cause, the result was a world of increasing biological complexity. Fish evolved from simpler chordate ancestors. Plants colonized the land, followed by arthropods and other invertebrates. Amphibians evolved from fish, reptiles from amphibians. Mammals and birds arose from different reptilian lineages, each transition building on what came before, each opening up new ecological niches and evolutionary possibilities. Throughout this long history, nervous systems evolved and became increasingly sophisticated. The earliest were simple nerve nets, like those found in modern jellyfish, capable of detecting environmental stimuli and coordinating basic behaviors. Over time, Centralized nervous systems emerged, with clusters of neurons that processed sensory information and coordinated more complex responses. Brains evolved as these neural clusters expanded and took on more functions. The evolutionary advantage of better information processing is clear. Animals that could more accurately sense their environments, more effectively coordinate their movements, more efficiently find food and mates and avoid predators, had higher chances of survival and reproduction. But brains are metabolically expensive. The human brain, which accounts for only about 2% of body weight, consumes roughly 20% of the body's energy. This high cost means that intelligence evolves only when its benefits outweigh its substantial energy demands. For most species throughout Earth's history, the optimal level of intelligence has been far below what we consider consciousness. The path to human-level intelligence was neither straight nor inevitable. It involved a complex interplay of environmental pressures, anatomical changes, social dynamics, and chance events. Our lineage, the hominins, diverged from that of chimpanzees roughly 7 million years ago. For millions of years, our ancestors were relatively small-brained, bipedal apes, not dramatically different in cognitive capacity from other great apes. The dramatic expansion of brain size and cognitive ability in our lineage began roughly 2 million years ago, with the emergence of the genus Homo. Several factors likely contributed to this evolutionary trajectory. Climate change created more variable and unpredictable environments, favoring greater behavioral flexibility. The shift to a more carnivorous diet provided more concentrated nutrients to fuel larger brains. Cooperative hunting and gathering created selective pressures for better social cognition. Tool use both required and further enhanced cognitive abilities. But perhaps the most significant factor was cumulative culture, the ability to learn from others and build on their innovations. This created a feedback loop. Larger brains enabled more complex culture. More complex culture created environments that favored larger brains. Each generation stood on the shoulders of those who came before, not just genetically but culturally. This cultural dimension introduces a new level of complexity to the evolution of intelligence. Unlike purely biological traits, culture can evolve much more rapidly than genes. It can also preserve and accumulate beneficial innovations more efficiently. Once a species crosses a certain threshold of cultural learning ability, its evolution is no longer purely biological, but technocultural, a hybrid process where genes and ideas co-evolve. Our own species, Homo sapiens, emerged roughly 300,000 years ago in Africa. For much of our early history, we were not dramatically different from other hominin species like Neanderthals. We made similar tools, lived in similar-sized groups, and had similar brain sizes. What set us apart was likely a unique combination of adaptations that enhanced our capacity for symbolic thinking, language, and social learning. The cognitive revolution, occurring roughly 70,000 years ago, marked a turning point. Suddenly, in evolutionary terms, our ancestors began producing art, elaborate burial rituals, more sophisticated tools, and other evidence of abstract thinking. They expanded across the globe, adapting to environments as diverse as the Arctic tundra and the Australian outback. They developed increasingly complex social structures and technologies. This revolution may have been driven by genetic changes that enhanced our language abilities or other aspects of cognition. It may have been a cultural threshold, where the accumulated knowledge and social complexity crossed a tipping point. Or most likely, it was a combination of biological and cultural factors, each amplifying the other in a powerful feedback loop. Whatever its cause, the cognitive revolution set humanity on a unique path. No other species on Earth has developed anything close to our level of technology or civilization. Despite millions of years of evolution, despite countless intelligent species from corvids to cetaceans to other primates, only humans have written symphonies, built cities, or wondered about their place in the cosmos. This uniqueness poses a profound question for our search. If intelligence like ours evolved only once on Earth, despite billions of years of opportunity, might it be similarly rare throughout the universe? Is there something about the path from chemistry to consciousness that makes our kind of intelligence an evolutionary oddity rather than an inevitable outcome? Several hypotheses might explain this rarity. First, there may be relatively few environmental contexts that favor the evolution of high intelligence. On Earth, it evolved most dramatically in social, tool using primates, but not in equally ancient lineages like sharks or insects. Perhaps the specific combination of environmental pressures that drive intelligence evolution is uncommon. Second, intelligence like ours may be just one of many possible adaptive peaks, and not necessarily the most likely one. Evolution has no foresight or direction. It does not aim for intelligence or complexity, but simply favors whatever traits enhance survival and reproduction in a given environment. For most species, other adaptations, from protective shells to camouflage to rapid reproduction, have proven more beneficial than large brains. Third, the evolution of intelligence may require a precise sequence of evolutionary innovations, each building on the last. The transition from prokaryotes to eukaryotes, the development of complex multicellularity, the evolution of sophisticated nervous systems, the emergence of social learning, all may be necessary preconditions. If any link in this chain is improbable, the entire sequence becomes vanishingly rare. Fourth, intelligence evolution may be frequently interrupted by extinction events. The history of life on Earth is punctuated by mass extinctions that have repeatedly reset the evolutionary clock. The dinosaurs might have eventually evolved intelligence had they not been wiped out 65 million years ago. If extinction events are common throughout the universe, they may repeatedly end promising evolutionary lineages before they achieve technology. These considerations suggest that while simple life might be common in the universe, and even complex multicellular life might exist on many worlds, technological civilizations like our own may be exceedingly rare. The path from chemistry to consciousness may be so difficult, so contingent on unlikely events and specific circumstances, that we might indeed be among the first to walk it successfully. But there is an alternative perspective. Perhaps intelligence and civilization have evolved many times throughout the cosmos, but follow different paths than our own. We tend to imagine alien intelligence as similar to ours, embodied in individual organisms with brains, sensory organs, and manipulative appendages. But consciousness might take radically different forms. Consider the octopus, an intelligent creature whose nervous system is distributed throughout its body, with more neurons in its arms than in its central brain. Or slime molds, seemingly simple organisms that can solve complex spatial problems despite lacking neurons entirely. Or the collective intelligence of social insect colonies, where thousands of relatively simple individuals create a superorganism capable of sophisticated behavior. Alien intelligence might be even more divergent from our own. Perhaps it resides in planet-spanning networks of fungal-like organisms, or in the complex chemistry of living oceans, or in symbiotic collectives of different species, or in forms so different from life as we understand it that we struggle to even conceptualize them. Such intelligences might not build radio telescopes or spacecraft. They might not create technology recognizable to us as such. They might communicate in ways we cannot detect or comprehend. They might exist right now, throughout the galaxy or beyond, while remaining effectively invisible to our search methods. This possibility highlights a limitation in how we think about the question of first civilization. We tend to define civilization in human terms, looking for analogues to our own technology, communication, and social structures. But consciousness, intelligence, and even technology might take forms utterly alien to our experience or understanding. Still, there are reasons to think that at least some aspects of intelligence and technology might be universal. The laws of physics and chemistry are the same throughout the cosmos. Mathematics is an objective reality that any sufficiently advanced intelligence would likely discover. Certain technological solutions, like using electromagnetic waves for communication or rockets for space travel, are based on physical principles that would apply anywhere. If technological civilizations like our own have emerged elsewhere in the universe, they would likely face many of the same challenges and opportunities that we do. They would need to harness energy, process and transmit information, and overcome the limitations of their biology. The solutions they develop might differ in details, but share fundamental principles with our own. This brings us to a crucial insight: the transition from chemistry to consciousness, from simple molecules to technological civilization, involves a series of steps of increasing improbability. Each step is a filter that reduces the number of worlds that progress to the next level. This concept, known as the Great Filter, may help explain why we do not observe evidence of other civilizations, despite the apparent abundance of potentially habitable worlds. If the great filter lies in our past, in the difficult transitions from chemistry to life, from prokaryotes to eukaryotes, from simple to complex multicellularity, from animals to intelligence, then we have already passed through the eye of the needle. We may indeed be among the first technological civilizations in our galaxy or beyond, rare pioneers in a largely lifeless, or at least technology-less cosmos. But if the great filter lies in our future, in challenges that technological civilizations typically fail to overcome, then the silence of the cosmos becomes an ominous warning. Perhaps societies typically destroy themselves once they develop certain technologies. Perhaps they face insurmountable resource limitations or environmental degradation. Perhaps they encounter threats we have not yet recognized. The transition from chemistry to consciousness that we have navigated, from the first organic molecules to our current civilization, may be just the beginning of an even more difficult journey. If we are indeed among the first technological civilizations in the cosmos, we may be the first to face whatever filters lie ahead. Our success or failure might help determine whether the universe ultimately becomes filled with consciousness and civilization, or remains largely silent and empty. As we ponder these possibilities, we must recognize the profound responsibility that comes with being potentially among the first. If technological civilizations are rare because the path to them is so difficult, then each such civilization represents an extraordinary achievement, a precious spark of consciousness and complexity in an otherwise largely unconscious cosmos. The emergence of minds capable of understanding the universe, of appreciating beauty, of creating art and music and science and philosophy, may be among the rarest and most valuable phenomena in existence. If we are indeed among the first, then we carry the responsibility of pioneers, of caretakers for something precious and fragile and possibly unique, at least in our cosmic neighborhood. This perspective shifts how we might think about the silence of the cosmos. Perhaps we do not hear other voices, not because they have fallen silent through catastrophe, but because we are truly among the first to speak. Perhaps the silence is not a warning but an opportunity, a vast open frontier awaiting exploration and the spread of consciousness. The journey from chemistry to consciousness that has occurred on Earth may be just beginning in the broader cosmos. The ingredients for life are everywhere, but the recipe for minds like ours may be only now being followed in scattered locations across the galaxy. We may be early risers in a universe still largely asleep, the first stirrings of awareness in a cosmos that will, in time, be filled with many voices. This possibility, that we are not the last of many failed civilizations but among the first of many yet to come, offers a profoundly hopeful perspective on our cosmic silence. It suggests that our civilization may have the extraordinary fortune and responsibility of helping to shape the future development of consciousness in our galaxy or beyond. If we are indeed among the first, then the choices we make now, as we take our first tentative steps beyond our planetary cradle, may echo across cosmic time. They may influence the development of countless future civilizations, either by direct contact or by example. The path we chart may become a guide for others who awaken later, facing their own transitions from chemistry to consciousness, from planetary civilizations to cosmic ones. In this view, the silence of the cosmos is not a mystery to be solved, but a canvas awaiting our contribution. We may indeed be the first civilization the universe has ever created, or among the very first. And if so, we stand at the dawn of a new phase in cosmic evolution, one in which consciousness and purpose begin to shape the development of the cosmos itself. The universe, through us, and perhaps through others like us scattered rare and distant, has begun to wake up, to know itself, to wonder about its own existence and future. We are not merely in the universe, we are the universe becoming conscious of itself. And that may be the greatest miracle of all, the transformation from mindless chemistry to minds capable of contemplating their own origins and destiny. In the summer of 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to the possibility of extraterrestrial life and the recent spate of UFO sightings. After considering the vast age and size of the universe, with its hundreds of billions of stars in our galaxy alone, Fermi reportedly asked a simple yet profound question: where is everybody? This question, now known as the Fermi paradox, cuts to the heart of our inquiry. If the universe is so vast and so old, if the ingredients for life are widespread, if the laws of physics and chemistry are universal, then civilizations should have had ample time and opportunity to arise before our own. Yet we see no evidence of them, no signals, no artifacts, no visitors. Just silence and emptiness as far as our instruments can detect. The paradox emerges from a series of reasonable assumptions. First, that there is nothing special about Earth or our Sun. They are ordinary celestial bodies, one rocky planet among billions, one medium-sized star among hundreds of billions in our galaxy alone. Second, that life, once it emerges, naturally evolves toward greater complexity and intelligence through natural selection. Third, that intelligence eventually leads to technology, including the ability to communicate across interstellar distances and potentially to travel between stars. Given these assumptions, and the fact that many stars in our galaxy are billions of years older than our Sun, civilizations should have had time to arise, develop technology, and spread throughout the galaxy long before we appeared. Even at the relatively modest speed of our own early space probes, roughly 0.1% of the speed of light, a civilization could colonize the entire galaxy in a few tens of millions of years, a mere eye blink in cosmic time. Yet we see no evidence of such galactic civilizations, no engineering projects visible through our telescopes, no artificial radio signals detected by our antennas, no probes or artifacts in our solar system, no visitors to our world, despite decades of claimed sightings that, upon investigation, inevitably resolve to more mundane explanations. This silence is puzzling and demands explanation. Over the decades since Fermi first posed his question, scientists and philosophers have proposed numerous potential resolutions to the paradox. These can be broadly categorized into several groups, each with its own implications for our question of whether we might be the first civilization. The first category suggests that civilizations are extremely rare. Perhaps one or more of the steps from non-living matter to technological society is extraordinarily improbable. This is the great filter hypothesis we touched on in the previous chapter. If the filter lies in our past, in transitions we have already navigated, then we may indeed be among the first or even the only technological civilization in our galaxy. Several candidates for this filter have been proposed. Perhaps the emergence of life itself is vanishingly rare, occurring on only a tiny fraction of potentially habitable worlds. Perhaps the transition from prokaryotic to eukaryotic cells, which appears to have happened only once on Earth, is an exceptionally unlikely event. Perhaps complex multicellularity is rare, or the evolution of intelligence, or the development of technology. If any of these transitions has a probability of, say, 1 in a billion, then even in a galaxy with billions of potentially habitable planets, civilizations would be exceedingly rare. We might be alone in the Milky Way, or one of a handful of civilizations so widely separated in space and time that contact is unlikely. A second category of explanations suggests that civilizations are common, but short-lived. Perhaps technological societies inevitably destroy themselves once they reach a certain level of development. Nuclear weapons, biological warfare, nanotechnology, artificial intelligence, environmental degradation, all present existential risks that advanced civilizations must navigate. If most fail, the galaxy might be full of the ruins of dead civilizations, their brief flowering of technology too short to allow for interstellar expansion. This explanation is sobering, as it suggests that we may be approaching our own great filter, a challenge that most civilizations fail to overcome. The silence of the cosmos becomes a warning, a cemetery of failed civilizations that reached our level of development, but no further. Our future would depend on whether we can succeed where others apparently have failed. A third category proposes that civilizations exist but are not expanding or communicating in ways we can detect. Perhaps interstellar travel is simply too difficult or energy-intensive, limited by physics in ways we do not yet understand. Perhaps civilizations turn inward, creating virtual realities or pursuing other interests that do not involve physical expansion into space. Perhaps they exist in forms we would not recognize, such as post-biological artificial intelligences with motivations alien to our understanding. This possibility suggests that the galaxy might be home to many civilizations, each isolated on its home world or within its home system, either unable or unwilling to expand beyond. We might be surrounded by neighbors we cannot detect because they are not doing anything that would make them visible to our current observation methods. A fourth category, known as the zoo hypothesis, suggests that advanced civilizations exist but are deliberately avoiding contact with emerging societies like our own. Perhaps there is a galactic policy of non-interference, allowing young civilizations to develop without external influence. Perhaps we are in a nature preserve or zoo, being observed but not contacted. Perhaps civilizations typically go through a dangerous phase of development, and contact is avoided until they have passed through it safely. This hypothesis implies that we are not the first but rather among the most recent civilizations to emerge, still in our technological infancy compared to vastly older and more advanced societies that may be watching us from afar. It suggests that the silence we perceive is not the absence of others, but their deliberate choice, an imposed quarantine that might someday be lifted. A fifth category proposes that we are not looking correctly. Our search for extraterrestrial intelligence has been limited in scope and duration. We have thoroughly examined only a tiny fraction of our galaxy for artificial radio signals, and those searches have been constrained by our assumptions about how other civilizations might communicate. Perhaps they use technologies we have not yet discovered, or frequencies we have not monitored, or methods we cannot imagine. This explanation suggests that the silence is an illusion created by the limitations of our search. The universe might be filled with communications we cannot yet detect, like a primitive tribe unaware of the radio and television signals passing through their village. It implies that we are not necessarily the first, merely the first in our region, to use our particular technologies, while others may communicate in ways beyond our current understanding. A sixth category, often called the simulation hypothesis, proposes that what we perceive as the universe is actually a simulation created by an advanced civilization. In this scenario, the silence exists because the simulation does not include other civilizations, either to conserve computing resources or as part of the experimental design. We would not be the first actual civilization, but rather a simulated one created by the true first civilization, or one of its descendants. While this hypothesis might seem far-fetched, philosophers have argued that if any civilization ever develops the ability to create fully immersive simulations of conscious beings, the number of simulated consciousnesses would eventually far exceed the number of actual ones. Statistically, we would be more likely to be living in such a simulation than in base reality. The silence of the cosmos would then be an artifact of the simulation's parameters rather than a reflection of the true universe. A seventh category, termed the early bird hypothesis, suggests that we are not the first, but among the first civilizations to emerge in our galaxy. Perhaps conditions for complex life have only recently become favorable in cosmic terms. Perhaps most stars in the galaxy are not conducive to hosting planets with stable environments needed for intelligent life to evolve. Perhaps cosmic events such as gamma-ray bursts or supernovae have periodically sterilized large regions of the galaxy, and only recently has a long enough period of relative calm allowed technological civilizations to emerge. This explanation places us not as the very first, but in the inaugural wave of galactic civilizations. It suggests that the silence is temporary, that we and others like us are just now reaching the threshold of potential interstellar communication and travel. The galaxy might soon, in cosmic terms, begin to fill with the signals and artifacts of multiple emerging civilizations, ours among them. These proposed resolutions to the Fermi paradox each have different implications for our question about being the first civilization. Some suggest we might indeed be first, or at least among the first few. Others propose that we are far from first but isolated from our predecessors by physics, biology, choice, or limitations in our search methods. To evaluate these possibilities, we must consider not just whether they are logically consistent, but whether they align with our observations and scientific understanding. We must also consider whether they rely on one unlikely assumption or many, applying Occam's razor to avoid unnecessarily complex explanations. The rareness of civilizations due to one or more highly improbable steps in their development is perhaps the simplest explanation. It requires only that at least one transition in the path from non-living matter to technological society be extremely unlikely. Given what we know about the apparently singular nature of several transitions in Earth's evolutionary history, this has significant plausibility. The explanation that civilizations are common but short-lived also has concerning plausibility. As we develop more powerful technologies, we create more ways to cause our own extinction. Nuclear weapons have existed for less than a century, and we have already come close to catastrophic conflict multiple times. Climate change, engineered pandemics, artificial intelligence, and other technologies we have not yet imagined may pose even greater threats. If most civilizations fail to navigate these dangers, their brevity would explain their apparent absence. The idea that civilizations exist but do not expand or communicate in detectable ways requires us to assume that either interstellar travel and communication are far more difficult than our current understanding suggests, or that virtually all civilizations choose not to expand despite having the capability. Either assumption seems to require a high degree of consistency across diverse civilizations, which is less parsimonious than assuming civilizations are simply rare. The zoo hypothesis requires an even greater stretch, as it assumes not only that multiple advanced civilizations exist, but that they all adhere to a policy of non-interference and have the means to enforce it perfectly across vast distances and timescales. It also assumes that not a single civilization has broken ranks in potentially millions or billions of years, which seems implausible given the diversity we would expect among independently evolved intelligences. The possibility that we are not looking correctly is valid, but limited as an explanation. While our search has indeed been constrained by time, resources, and assumptions, some means of detecting advanced civilizations should be available to us if they exist in large numbers and have been active for millions or billions of years. Any civilization that extensively colonizes or engineers its environment should leave signs visible to even our limited instruments, unless they deliberately hide all evidence of their existence. The simulation hypothesis, while intriguing philosophically, offers little scientific traction. It is essentially unfalsifiable, as any evidence we might gather could be part of the simulation. While we cannot dismiss it entirely, it serves more as a philosophical thought experiment than a scientifically testable explanation for the Fermi paradox. The early bird hypothesis has gained support from recent astronomical findings. We now know that the cosmic abundance of heavy elements has increased over time, potentially making the formation of rocky planets more common in recent cosmic history. Research suggests that stars in certain regions of galaxies, particularly areas with moderate stellar density and fewer nearby supernovae or gamma-ray bursts, may be more conducive to complex life. If our region of the galaxy has only recently become favorable for technological civilizations, we might indeed be among the first to emerge. Given these considerations, the most parsimonious explanations for the Fermi paradox appear to be either that civilizations are genuinely rare due to one or more improbable steps in their development, or that they are relatively short-lived, or some combination of these factors. Either explanation is consistent with the possibility that we are, if not the very first civilization in the galaxy, at least among the first few. This conclusion is both sobering and exhilarating. Sobering, because it suggests that the path we have traveled from simple chemistry to consciousness and civilization is extraordinarily rare or fragile. Exhilarating, because it implies that we may have the incredible privilege of being pioneers in a largely unexplored cosmos. If we are among the first, the silence we perceive is not a warning, but an opportunity. The galaxy is not a graveyard of failed civilizations, but a vast frontier, awaiting exploration. The absence of others does not mean we are doomed to fail, but that we have the chance to succeed, where perhaps no one has succeeded before, to become the ancestors that future civilizations will search for evidence of, just as we now search for evidence of our predecessors. But this conclusion comes with profound responsibility. If technological civilizations are rare because the great filter lies in our future, we must navigate those challenges with wisdom and foresight. We must develop the technologies, institutions, and values that will allow us to avoid self-destruction and achieve long-term sustainability. We must recognize that we may be carrying the torch of consciousness and civilization, not just for humanity, but for our corner of the cosmos. Even if the great filter lies behind us, making our existence an improbable miracle, we still bear the responsibility of preserving what may be an extraordinarily rare phenomenon in the universe: the emergence of minds capable of understanding the cosmos, of creating art and science and philosophy, of extending compassion beyond kin and kind, may be among the most precious developments in cosmic history. In either case, the Fermi paradox challenges us to think deeply about our place in the universe and our potential future. It reminds us that in a cosmos of hundreds of billions of galaxies, each with hundreds of billions of stars, silence and emptiness are themselves profound mysteries, demanding explanation. The absence of others, far from diminishing our significance, may highlight the extraordinary rarity and value of what we represent: consciousness and civilization in a universe that may contain precious little of either. As we continue our search for signs of other civilizations, we must keep an open mind about the many possible resolutions to the Fermi paradox. We must expand and refine our search methods, challenging our assumptions about how advanced civilizations might manifest. We must consider not just radio signals but technosignatures of all kinds, from atmospheric modifications to waste heat to megastructures. At the same time, we must recognize that the answer to Fermi's question, "Where is everybody?" may turn out to be simply, "We are among the first." The silence of the cosmos may not be a paradox at all, but rather the background against which the remarkable rarity and preciousness of our existence stands in sharp relief. The emptiness we perceive may be not a failure of imagination or observation, but a truth about the universe. A truth that places upon us the extraordinary responsibility and opportunity of being among the universe's first awakening minds. The Fermi paradox thus returns us to our central question: are we the first civilization the universe has ever created? While we cannot answer with certainty, the paradox suggests that we may indeed be, if not the very first, then among an inaugural generation of technological civilizations in our galaxy. The silence we observe, while not conclusive proof, is consistent with this possibility, especially when combined with our emerging understanding of the many improbable steps that led from simple chemistry to human civilization. In the chapters that follow, we will explore this possibility more deeply, examining the implications of being first, the future of our search for others, and the meaning this perspective might hold for our self-understanding and our cosmic future. For if we are indeed among the first conscious, technological species in our galaxy, then we stand not at the end of a long evolutionary process, but at the beginning of a potentially vast cosmic story, a story in which we may play a founding role as the universe itself awakens to consciousness and begins to contemplate its own existence. Throughout our exploration, we have circled around a profound possibility, one that challenges our intuition about our place in the cosmos. Could humanity truly be among the first technological civilizations in the universe? The vastness of space and time seems to argue against it. With hundreds of billions of stars in our galaxy alone, many of them billions of years older than our Sun, surely others must have walked this path before us. And yet, the silence persists. Let us examine more closely the evidence for what astronomers call the early universe hypothesis, the idea that we may be among the earliest technological civilizations to emerge, not just in our galaxy, but perhaps in the observable universe. This hypothesis does not necessarily claim we are the very first, but rather that we are part of an initial wave of sentient, technological species, arising near the beginning of the habitable era of cosmic history. The first line of evidence comes from our deepening understanding of cosmic chemical evolution. While the universe is indeed ancient at 13.8 billion years, the elements necessary for life as we know it were not present in the beginning. The Big Bang produced only the lightest elements, hydrogen and helium, with trace amounts of lithium. Every other element in the periodic table, from carbon to oxygen to iron to uranium, was forged later, in the nuclear furnaces of stars, or in their explosive deaths. The first generation of stars contained virtually no heavy elements. They were composed almost entirely of hydrogen and helium. These stars lived fast and died young, their immense gravity crushing their cores until nuclear fusion began. In their deaths, whether as supernovae or more exotic stellar events, they scattered the first heavy elements into space, seeding the gas clouds from which the next generation of stars would form. This process of stellar nucleosynthesis is cumulative. Each generation of stars inherits the elements created by previous generations and adds to that inventory through its own nuclear processes. The cosmic abundance of heavy elements, what astronomers call metallicity, has steadily increased over the history of the universe. In the early universe, planets like Earth, rich in iron, silicon, oxygen, and other heavy elements, simply could not form because these elements were too rare. Recent observations of ancient galaxies, made possible by instruments like the Webb Space Telescope, have revealed that the cosmic abundance of elements heavier than helium has increased by a factor of 20 or more over the history of the universe. Stars forming today incorporate far more heavy elements than those that formed billions of years ago. Since rocky planets require substantial amounts of these elements, truly Earth-like worlds may have been rare or non-existent in the early universe. This chemical evolution suggests a timeline for the potential emergence of life and civilization. The first stars formed about 200 million years after the Big Bang. The first heavy elements were scattered into space shortly thereafter, but it would take many generations of stars, living and dying, to build up enough heavy elements for rocky planets to form in significant numbers. This process likely took billions of years. The oldest known Earth-like exoplanet discovered so far, Kepler 452b, orbits a star that is about 6 billion years old, only about 1.5 billion years older than our Sun. While older, potentially habitable worlds may exist, the increasing metallicity of the universe over time suggests that Earth, like planets, have become more common in relatively recent cosmic history. Even if rocky planets formed earlier, they may have faced other challenges to the development of complex life. High-energy events like gamma-ray bursts, supernova explosions, and quasar outbursts were more common in the early universe. These events can strip planetary atmospheres and bombard surfaces with lethal radiation, potentially sterilizing large regions of galaxies. The cosmic environment has become progressively more hospitable to complex life over time, as these violent events have become less frequent. A second line of evidence comes from our evolving understanding of habitable zones, not just around stars, but within galaxies. Just as there is a Goldilocks zone around stars where planets are neither too hot nor too cold for liquid water, there appear to be regions within galaxies that are more conducive to life than others. The inner regions of galaxies are densely packed with stars, increasing the frequency of catastrophic events like supernovae that could threaten developing life. They also typically contain supermassive black holes that, when active, bathe their surroundings in intense radiation. The outer fringes of galaxies, conversely, contain fewer heavy elements, making Earth-like planets less common. The most favorable region, what some astronomers call the galactic habitable zone, tends to be in the intermediate regions of spiral galaxies, like our own location in the Milky Way. These areas have enough heavy elements for rocky planets, while avoiding the most dangerous cosmic neighborhoods. But the extent of these habitable zones has likely increased over time as heavy elements have spread more widely throughout galaxies and violent events have become less frequent. A third line of evidence comes from the stability of stars themselves. Not all stars provide equally hospitable environments for life. The most massive stars burn hot and bright but live for only a few million years, hardly enough time for complex life to evolve. The smallest stars, red dwarfs, can live for trillions of years, but tend to be highly active in their youth, bathing their planets in sterilizing flares and coronal mass ejections. Stars like our Sun, what astronomers classify as G-type main sequence stars, strike a balance. They are stable over long periods, allowing planetary environments to remain hospitable for the billions of years it may take for complex life and intelligence to evolve. They provide enough energy to power robust biospheres without subjecting their planets to extreme radiation environments, and they live long enough, about 10 billion years, for complex evolution to unfold. However, G-type stars compose only about 7% of all stars in our galaxy. The vast majority, perhaps 75%, are the smaller, longer-lived, but more active red dwarfs. If red dwarfs are significantly less hospitable to complex life than previously thought, this would dramatically reduce the number of potentially life-bearing systems in the galaxy, especially in the earlier epochs of cosmic history, when even G-type stars were more active and less stable. A fourth line of evidence comes from a deeper understanding of the multiple stages of complexity that life on Earth passed through before reaching our level of organization. As we explored in Chapter 4, The path from simple chemistry to human civilization involved numerous transitions, some of which may have been highly improbable. The fossil record suggests that while simple, single-celled life emerged relatively quickly after Earth became habitable, complex multicellular life took far longer to appear. Single-celled organisms emerged by at least 3.7 billion years ago, but complex multicellular life with specialized tissues did not flourish until about 540 million years ago, more than 3 billion years later. If this pattern holds elsewhere, many worlds might harbor microbial life, but few would have progressed to complex multicellularity. Even after complex multicellular life emerged, the path to intelligence and technology was neither direct nor inevitable. Intelligent species have evolved multiple times on Earth, in lineages as diverse as cephalopods, corvids, cetaceans, and primates. But only one, our own, has developed civilization and technology. If intelligence like ours is the result of a highly specific evolutionary pathway, guided by particular environmental pressures and contingent events, it may be extremely rare even on worlds with complex multicellular life. These lines of evidence converge to suggest that the conditions favorable for technological civilizations may have become common only relatively recently in cosmic history. If Earth-like planets became abundant only in the last 5 to 7 billion years, if stable stellar environments suitable for complex life are relatively rare, if the path from simple life to technology involves multiple improbable steps, then we may indeed be among the first wave of technological civilizations in our galaxy or beyond. This perspective is further supported by considerations of the future habitability of the universe. Current models of cosmic evolution suggest that star formation will continue for trillions of years, albeit at a declining rate. The smallest, longest-lived stars, red dwarfs, can shine for up to 10 trillion years. Even after star formation eventually ceases, existing stars will continue to provide energy and potentially habitable environments for trillions more years. In total, the era of stars, the cosmic epoch during which planets could potentially support life as we know it, might last for 100 trillion years or more. If we place ourselves on this vast timeline, humanity appears not at the end but near the very beginning of the habitable lifetime of the universe. If the potentially life-supporting history of the cosmos will span 100 trillion years, and the universe is currently 13.8 billion years old, then we have arrived after just 0.014% of cosmic habitability has elapsed. From this perspective, we are not latecomers, but early birds, awakening near the dawn of the vast cosmic day. The stars and planets that exist now represent just the first tiny fraction of all that will ever form. The silence we perceive may not be the absence of others, but simply the quietness of a universe that is just beginning to wake up to consciousness and intelligence. This early universe hypothesis offers a resolution to the Fermi paradox that is both intellectually satisfying and empirically consistent with our observations. It explains the absence of evidence for other technological civilizations without requiring multiple unlikely assumptions. It aligns with our current understanding of cosmic chemical evolution, galactic habitable zones, stellar habitability, and biological complexity. And it places humanity in a remarkable position, not as an anomaly, but as a pioneering species in the opening chapters of cosmic intelligence. But this hypothesis also implies profound responsibilities. If we are among the first technological civilizations, our actions may influence the development of consciousness and intelligence throughout our galaxy and potentially beyond. The paths we chart, the technologies we develop, the values we embody, the mistakes we make or avoid, all may serve as precedents for those who come after us. Consider the possibility that we are not just exploring a galaxy already shaped by countless prior civilizations, but rather helping to determine what kind of galaxy future civilizations will inherit. Our decisions about space exploration, about the deployment of artificial intelligence, about the preservation or destruction of habitable environments, may echo across cosmic time, influencing the evolutionary and technological trajectories of species that have not yet emerged. The early universe hypothesis suggests that the future of intelligence in the cosmos is not predetermined, but open, not constrained by the patterns of countless prior civilizations, but relatively unwritten. We may be among the architects of a cosmic future that will unfold over timescales beyond human imagination, a future in which consciousness and intelligence might spread across the galaxy and perhaps the universe. This perspective transforms how we might think about our cosmic silence. Rather than a warning of some inevitable technological catastrophe that befalls all advanced civilizations, it becomes an opportunity, a vast cosmic frontier awaiting exploration and habitation. The absence of others does not mean we are doomed to fail, but that we have the chance to succeed where perhaps few or none have gone before. But skepticism is warranted whenever we find ourselves placed in a seemingly special position in the cosmos. Throughout scientific history, hypotheses that grant humanity a central or unique role have generally yielded to more modest understandings of our place in the universe. From the geocentric model that placed Earth at the center of creation, to the anthropocentric view that sees human intelligence as the pinnacle of evolution, our intuitions often flatter our significance more than the evidence justifies. Could the early universe hypothesis be another such error, a way of preserving human specialness in the face of cosmic silence? To address this concern, we must distinguish between being genuinely early and being central or special. The early universe hypothesis does not claim that humanity is the purpose or pinnacle of cosmic evolution, merely that we happen to exist during an early phase of habitable cosmic history due to the combination of factors we have examined. Consider an analogy. In a forest that will stand for 1,000 years, the first saplings to sprout are not more important or central to the forest's story than those that will grow later. They simply happen to emerge first due to the particular timing of seed dispersal, soil conditions, and other factors. Similarly, if humanity is among the first technological civilizations, it is not because we are cosmically privileged, but because someone had to be first, and the conditions for our emergence happen to coincide with the early phases of cosmic habitability. There are other alternatives to the early universe hypothesis that must be considered. Perhaps civilizations are common but short-lived, as discussed in our exploration of the Fermi paradox. Perhaps they exist, but are not expanding or communicating in ways we can detect. Perhaps our search has been too limited in scope and duration to find evidence that does exist. Each of these alternatives has its own plausibility and implications, and we cannot definitively rule them out. The early universe hypothesis is not a certainty, but a possibility, consistent with our current understanding. It is a hypothesis to be tested and refined through ongoing observation and exploration, not a conclusion to be accepted without question. If the early universe hypothesis is correct, however, the implications are profound. We may be witnessing the very beginning of cosmic intelligence, the first stirrings of the universe becoming aware of itself. We may be among the architects of a process that will unfold over millions or billions of years, as consciousness and technology spread from Earth to other worlds, and perhaps eventually to other star systems. This process is already beginning in its most preliminary forms. Our robotic probes have visited every planet in our solar system and numerous smaller bodies like asteroids and comets. Our radio and television signals, though too weak to be detected at interstellar distances without highly specialized equipment, have been expanding outward from Earth for about a century. Our nascent technologies for planetary exploration and terraforming, though still theoretical or in early development, point toward a future in which humanity might extend its presence beyond Earth. If we are indeed among the first, these modest beginnings may be the opening movements of a cosmic symphony. The silent emptiness we perceive may be not the aftermath of countless failed civilizations, but the quiet stage upon which the future of cosmic intelligence will unfold. The absence of others may not mean we are alone forever, but that we are early arrivers, pioneers in a universe that is just beginning to wake up. This perspective offers both hope and caution. Hope, because it suggests that the dangers of advanced technology are not inevitably catastrophic, that civilizations like ours may have the potential for long-term survival and expansion. Caution, because if we are among the first, we have few or no examples to learn from, no roadmaps left by predecessors who navigated the challenges we now face. As we continue our search for evidence of other civilizations, we must remain open to all possibilities. If we detect signals or artifacts from another technological species, it would demonstrate that we are not alone and potentially provide invaluable insights into how advanced civilizations develop and survive. It would be perhaps the most significant discovery in human history, establishing that the path from chemistry to consciousness has been walked at least twice in the cosmos. But if our search continues to yield silence, we should consider more seriously the possibility that we are indeed among the first. Not out of human exceptionalism or cosmic narcissism, but because the evidence of cosmic chemical evolution, galactic and stellar habitability, and biological complexity increasingly suggests that the conditions favorable for technological civilizations may have become common only in relatively recent cosmic history. If we are among the first, we bear the responsibility of pioneers. Our choices may influence not just our own future, but the development of cosmic intelligence itself. The technologies we create, the values we embody, the mistakes we make or avoid, all may serve as precedents or warnings for those who come after us. We may be setting the initial conditions for a process of cosmic awakening that will unfold over timescales far beyond human comprehension. This responsibility is simultaneously humbling and exalting. Humbling because it reminds us how much we still have to learn, how preliminary our understanding and technology remain compared to what may be possible. Exalting because it suggests that our existence, our consciousness, our civilization may be among the rarest and most precious phenomena in the current universe, the beginning of something extraordinary rather than a common or inevitable occurrence. The early universe hypothesis transforms our understanding of cosmic silence from a paradox to be solved into a canvas awaiting our contribution. It suggests that the emptiness we perceive is not the absence of what should be there, but the presence of possibility, the open space into which consciousness and intelligence are just beginning to expand. It places humanity not at the end of a long evolutionary process, but at the beginning of a potentially vast cosmic story, a story in which we may play a founding role. As we look up at the silent stars, we might be seeing not a cosmos that has already played out its drama of intelligence, but one that is just setting the stage. The darkness between the stars may be not the graveyard of failed civilizations, but the fertile void from which countless future civilizations might someday emerge. And our own small light of consciousness and technology, burning on our pale blue dot, may be not the last flicker of a dying kind, but among the first sparks of a cosmic awakening that will unfold over billions of years to come. In our exploration of the cosmic silence, one concept has emerged repeatedly as a possible explanation. Astronomer Robin Hanson termed it the Great Filter, a hypothesis that addresses the apparent contradiction between the seemingly high probability of extraterrestrial intelligence and the lack of evidence for its existence. The Great Filter proposes that somewhere along the path from non-living matter to spacefaring civilization, there exists at least one developmental step that is extraordinarily difficult or improbable, a filter so challenging that few or perhaps no species successfully navigate it. The concept is powerful because it offers a framework for understanding our cosmic solitude without requiring us to abandon our understanding of physics, chemistry, or biology. It acknowledges the vastness of space and time, while suggesting that the emergence of technological civilizations might nevertheless be vanishingly rare. Most importantly, it forces us to confront a profound question. Is the Great Filter behind us, in evolutionary steps we have already passed through? Or does it lie ahead, in challenges that technological civilizations typically fail to overcome? The answer to this question has existential significance for humanity. If the Great Filter lies in our past, in transitions we have already navigated, then we may indeed be among the first civilizations in our galaxy or beyond, rare pioneers in a largely lifeless, or at least technology-less cosmos. But if the Great Filter lies in our future, in challenges that technological civilizations typically fail to overcome, then the silence of the cosmos becomes an ominous warning. We may be approaching the very filter that has prevented others from expanding into the stars. Let us examine the potential Great Filters, both those we may have passed and those we might yet face, to better understand our cosmic position and prospects. The first potential Great Filter is the emergence of life itself, the transition from non-living chemistry to self-replicating, evolving systems. On Earth, this transition appears to have occurred relatively quickly in geological terms, perhaps within a few 100 million years after conditions became favorable. This suggests that abiogenesis, the origin of life, might not be extraordinarily difficult given the right conditions. However, we have only one example to judge from, our own planet, we do not know if life has emerged elsewhere in our solar system or beyond. The apparent rapidity of life's emergence on Earth could be misleading, a statistical anomaly rather than a representative case. If abiogenesis requires a highly specific sequence of chemical events, with a vanishingly small probability of occurrence, it could indeed be a great filter that few planets pass through. The second potential filter is the transition from simple, prokaryotic cells to more complex eukaryotic cells, with specialized internal structures. On Earth, this transition took roughly 2 billion years after the emergence of life, suggesting it may be more difficult than abiogenesis itself. The evolution of eukaryotes appears to have been a singular event in Earth's history, occurring when one type of prokaryotic cell engulfed another, eventually leading to a symbiotic relationship where the engulfed cell became an organelle, the mitochondrion. If this kind of endosymbiosis is indeed rare, requiring highly specific circumstances or a precise sequence of unlikely events, it could be a significant filter. Worlds with simple, prokaryotic-like life might be relatively common, while those with complex eukaryotic analogues might be exceedingly rare. The third potential filter is the development of complex multicellularity, the transition from single cells or simple colonies to organisms with differentiated tissues and specialized cells. While simple multicellularity has evolved independently many times on Earth, complex multicellularity with substantial cell differentiation appears to have evolved only about a dozen times, and only in eukaryotic lineages. The relative rarity of this transition, even among eukaryotes, suggests it may be another significant filter. If complex multicellularity requires specific genetic innovations or environmental conditions that rarely align, many worlds might harbor single-celled or simply multicellular life, but few would develop the complex organisms that could eventually evolve intelligence. The fourth potential filter is the evolution of intelligence itself, particularly the kind of general intelligence capable of developing technology. On Earth, while many lineages have evolved forms of intelligence, only one, our own, has developed mathematics, science, and technology. This suggests that intelligence like ours may not be an inevitable outcome of evolution, but rather a highly contingent development, relying on specific environmental pressures and evolutionary pathways. If technological intelligence requires a precise combination of factors, such as the right appendages for manipulating tools, the right sensory systems, the right social structures, and the right environmental challenges to drive cognitive development, it may be extraordinarily rare even on planets with complex multicellular life. Many worlds might harbor intelligent species, but few would develop the specific kind of intelligence needed for technology. The fifth potential filter is the transition from intelligence to civilization, particularly a technological civilization capable of interstellar communication or travel. On Earth, our species existed for hundreds of thousands of years before developing agriculture, cities, writing, and eventually advanced technology. This transition was neither inevitable nor straightforward, but depended on specific geographic, climatic, and cultural factors. If the development of civilization requires a narrow range of conditions, such as the right distribution of domesticable plants and animals, the right geography for trade and cultural exchange, or the right climate stability for agricultural development, it may be rare even among intelligent species. Many worlds might harbor intelligent beings, but few would develop the civilizations necessary for interstellar contact. These potential filters in our past, from the emergence of life to the development of civilization, might individually or collectively explain our apparent cosmic solitude. If any one of them has a probability of, say, 1 in a billion, then even in a galaxy with billions of potentially habitable planets, technological civilizations would be extraordinarily rare. We might be alone in the Milky Way, or one of a handful of civilizations so widely separated in space and time that contact is unlikely. This possibility, that we have already passed through the Great Filter, is both reassuring and humbling. Reassuring, because it suggests that the challenges of advanced technology are not inevitably catastrophic, that civilizations like ours may have the potential for long-term survival and expansion. Humbling, because it implies that our existence, our consciousness, our civilization, may be among the rarest and most precious phenomena in the cosmos. But there is another possibility, one that casts a shadow over our future. The Great Filter might lie not in our past, but in our future, in challenges that technological civilizations typically fail to overcome. This possibility is more disturbing, as it suggests that we may be approaching the very filter that has prevented others from expanding into the stars. What might constitute a great filter in our future? Several candidates have been proposed, each with its own plausibility and implications. The first is self-destruction through advanced technology. As civilizations develop more powerful technologies, they create more ways to cause their own extinction. Nuclear weapons have existed for less than a century, and we have already come close to catastrophic conflict multiple times. Other technologies on our horizon, from engineered pandemics to artificial intelligence to nanotechnology, may pose even greater existential risks. If most technological civilizations destroy themselves once they reach a certain level of development, this would explain the cosmic silence. The galaxy might be full of planets where life evolved, intelligence emerged, and civilizations arose, only to destroy themselves before they could expand beyond their home worlds or establish lasting interstellar communication. The second potential future filter is resource depletion or environmental collapse. Technological civilizations require enormous resources, from metals and minerals to energy sources to habitable environments. The development of technology often involves extracting these resources at unsustainable rates, or producing waste that damages the very systems that support the civilization. If most technological civilizations exhaust their resources or damage their environments beyond repair before developing sustainable alternatives or expanding beyond their home planets, this too would explain the cosmic silence. The galaxy might be littered with worlds where civilizations rose and fell, leaving only ruins or simplified successor species in their wake. The third potential future filter is natural catastrophe. Even without self-inflicted damage, civilizations face numerous natural threats. Asteroid or comet impacts, supervolcanic eruptions, gamma-ray bursts, nearby supernovae, or extreme climate shifts could all potentially end a civilization before it develops the capability to prevent such disasters or establish self-sustaining colonies beyond its home world. If such catastrophes typically occur before civilizations can protect themselves or expand beyond their vulnerability, this would explain why we do not see evidence of galactic civilizations. The cosmos might be too dangerous an environment for most civilizations to survive long enough to become detectable across interstellar distances. The fourth potential future filter is inherent limitations to expansion. Perhaps interstellar travel or communication is simply too difficult, too energy-intensive, or too time-consuming to be practical, even for highly advanced civilizations. Perhaps the laws of physics place fundamental constraints on technology that make galactic expansion impossible or impractical. If civilizations typically reach a technological plateau that prevents significant expansion beyond their home systems, this would explain why we do not observe evidence of galactic-scale engineering or colonization. The universe might contain many civilizations, each isolated in its home system, unable to overcome the vast distances between stars. The fifth potential future filter is post-biological transition. Perhaps most technological civilizations eventually transition from biological to artificial or hybrid forms, developing artificial intelligence or uploading their consciousness to more durable substrates. Such post-biological civilizations might have motivations and behaviors very different from those we would expect of beings like ourselves. If post-biological civilizations typically turn inward rather than outward, creating virtual worlds or pursuing goals that do not involve physical expansion, this would explain the absence of visible megastructures or colonization efforts. The universe might harbor many such civilizations, but they might be uninterested in the kind of cosmic engineering we would expect to detect. These potential future filters, from self-destruction to post-biological transition, might individually or collectively explain why we do not observe evidence of advanced civilizations, despite the apparent abundance of potentially habitable worlds. If any one of them typically prevents civilizations from expanding beyond their home systems or maintaining interstellar visibility for long periods, the cosmos would appear largely empty even if intelligence and civilization are relatively common. This possibility, that the Great Filter lies in our future, is more troubling than the alternative. It suggests that we are approaching challenges that most civilizations fail to overcome, that the path ahead contains obstacles so severe that they typically end technological society before it can expand to the stars. Yet even this darker interpretation offers some hope. If we can identify the most likely future filters, we might be able to navigate them more successfully than others before us. If we understand the dangers of advanced technology, resource depletion, environmental damage, or natural catastrophe, we might develop the wisdom, institutions, and technologies needed to survive them. Indeed, the very awareness of potential great filters might be a crucial advantage in overcoming them. If we recognize that technological civilizations might typically destroy themselves, deplete their resources, or fall victim to natural disasters, we might take these threats more seriously and invest more heavily in mitigation strategies. The concept of the Great Filter, far from being merely an abstract explanation for cosmic silence, might itself become a tool for survival. This leads to a profound possibility. Perhaps the Great Filter is not a single insurmountable obstacle, but a series of challenges that civilizations must navigate. Perhaps what makes technological civilizations rare is not any individual step, but the compounding improbability of passing through all the necessary stages without catastrophe. In this view, each transition, from the emergence of life to the development of sustainability, represents a filter that reduces the number of worlds that progress to the next level. The combined effect of these multiple filters, each removing perhaps 90% or 99% or 99.9% of potential candidates, would be to make technological civilizations vanishingly rare, even in a galaxy of hundreds of billions of stars. This multiple filter perspective aligns with our emerging understanding of astrobiology, evolutionary biology, and the history of technology. It suggests that simple life might be relatively common in the universe, complex multicellular life less so, intelligent life rarer still, and technological civilizations capable of interstellar communication or travel exceedingly rare. It also aligns with the early universe hypothesis we explored in the previous chapter. If multiple filters reduce the probability of technological civilization to something astronomically small, and if the conditions favorable for such civilizations have become common only relatively recently in cosmic history, then we may indeed be among the first or at least among the earliest wave of technological species. The implications of the Great Filter hypothesis, whether it lies behind us or ahead of us or both, are profound for our understanding of our place in the cosmos and our potential future. If we have already passed through the primary filters, we may be among the most precious phenomena in the current universe, rare conscious observers in a cosmos that is only beginning to wake up. If the primary filters lie ahead, we face challenges of potentially existential significance, obstacles that we must navigate with wisdom and foresight if we are to avoid the fate that may have befallen others. In either case, the concept of the Great Filter transforms how we might think about the silence of the cosmos. It suggests that this silence is neither a paradox to be solved, nor a mystery beyond comprehension, but rather a consequence of the extraordinary difficulty of the path, from chemistry to consciousness to civilization to cosmic expansion. The emptiness we perceive may be not an anomaly, but the expected outcome of a universe where each step toward technological intelligence faces steep odds. This understanding does not diminish the significance of our search for other civilizations. Indeed, it heightens it. If technological societies are as rare as the Great Filter hypothesis suggests, then any evidence of another would be of immeasurable value. It would demonstrate that the filters can be passed through at least twice, offering potential insights into how civilizations might survive and thrive. It would be perhaps the most significant discovery in human history, establishing that the path from matter to mind to meaning has been walked at least twice in the cosmos. But even if our search continues to yield silence, the Great Filter hypothesis offers a framework for understanding that silence without despair. It suggests that the emptiness we perceive is not a judgment on our significance, but rather a testament to the remarkable improbability of our existence. We may be rare, but not alone forever, early but not isolated eternally. Other civilizations may emerge in time, passing through the same filters we have navigated, facing the same challenges we now confront. If we can identify and overcome the potential filters in our future, we may have the extraordinary privilege of helping to ensure that consciousness and intelligence spread beyond our pale blue dot. We may be among the architects of a process that will unfold over millions or billions of years as the silent cosmos gradually awakens to awareness and purpose. The Great Filter Hypothesis thus returns us to our central question: are we the first civilization the universe has ever created? While we cannot answer with certainty, the concept of multiple improbable filters, some in our past and perhaps some in our future, suggests that we may indeed be, if not the very first, then among a pioneering few. The silence we observe may be not the absence of what should be there, but the presence of possibility, the open canvas upon which the future story of cosmic intelligence has only just begun to be written. Thus far, we have explored the possibility that humanity might be among the first technological civilizations in our galaxy, or perhaps the universe. We have considered the increasing metallicity of the cosmos over time, the multiple improbable steps from chemistry to consciousness, and the concept of great filters that might make technological societies exceedingly rare. These perspectives suggest that the silence we observe might be the expected state of a universe just beginning to wake up to intelligence. But there is another possibility we must consider, one that challenges our interpretation of cosmic silence. Perhaps we are not among the first. Perhaps ancient civilizations have risen and fallen across the galaxy or beyond, leaving traces too subtle or too alien for us to have detected with our brief search and limited technology. Perhaps the cosmos is not silent, but speaking in whispers we have not yet learned to hear. What might remain of civilizations that flourished millions or billions of years ago? What traces might they have left that could potentially be detected across the vast gulfs of space and time? And why have our searches thus far failed to find convincing evidence of such ancient intelligences? To approach these questions, we must avoid the trap of excessive anthropocentrism, of assuming that other civilizations would necessarily follow paths similar to our own. Advanced technological societies might develop along trajectories we can barely imagine, utilizing technologies and pursuing goals utterly foreign to our experience. Their traces might be all around us, yet invisible to eyes that do not know what to look for. Let us consider what traces various types of ancient civilizations might leave, from those only modestly more advanced than our own, to those that might have achieved capabilities currently relegated to the realm of science fiction. A civilization at a level comparable to humanity's current development would leave certain detectable traces. Radio and television signals would propagate outward from their home world at the speed of light. Atmospheric changes caused by industry and agriculture might be detectable with sensitive spectroscopy. Space exploration would leave artifacts on nearby worlds, from landing craft to rovers to debris. These traces, while modest, could potentially be detected by a sufficiently advanced observer. Our own civilization has existed at a technological level capable of producing such traces for only about a century, a cosmic eye blink. If ancient civilizations remained at a similar level for comparable periods before either advancing further or declining, their detectable electromagnetic emissions would have long since passed Earth, reaching us only if they existed within the last few thousand years, and within a few thousand light-years of our solar system. Given the vastness of the galaxy, such a spatial and temporal coincidence would be highly improbable. A more advanced civilization, one that had mastered interplanetary travel and large-scale engineering of its home system, would leave more substantial traces. Artificial satellites and space stations might orbit various bodies in their system. Mining operations might leave visible changes on asteroids, moons, or planets. Large-scale energy collection systems, such as solar arrays, might be detectable through their heat signatures or visible structures. Such a civilization, while far more visible than one confined to its home planet, would still be difficult to detect across interstellar distances unless we were specifically observing their star system with our most sensitive instruments. The number of stars in our galaxy is so vast, and our observational resources so limited, that we have closely examined only a tiny fraction for such signs. The traces of dozens or hundreds of such civilizations might exist within the Milky Way, yet remain undetected due to the sheer scale of the search space. A still more advanced civilization, one capable of interstellar travel or communication, would leave traces that could potentially span multiple star systems. probes or beacons might be placed in promising systems to monitor for the emergence of new intelligent species. Way stations might be established along routes between colonies or outposts. Communication networks might send signals between distant stars, creating patterns of electromagnetic radiation that might appear artificial to a sufficiently sensitive observer. However, even such an advanced civilization would be constrained by the vast distances between stars and the finite speed of light. Unless they had developed physics beyond our current understanding, their expansion and communication would be limited to subluminal velocities. A civilization that emerged in a distant part of the galaxy millions of years ago might have spread to thousands of star systems, yet never reached our cosmic neighborhood. Their signals might have passed Earth long before humans evolved, or might not yet have arrived. The most advanced civilization we can reasonably conceive, one that had mastered technologies far beyond our current capabilities, might leave the most extensive, yet also the most alien traces. Such a civilization might be capable of engineering on a stellar or even galactic scale, harnessing the energy of entire stars or utilizing the resources of countless worlds. They might have transcended biology entirely, existing as artificial intelligences or in forms we cannot comprehend. The theoretical physicist Freeman Dyson proposed that such advanced civilizations might construct spheres or swarms around stars to capture most or all of their energy output. These Dyson structures, as they have come to be called, would be among the most detectable artifacts of an advanced civilization. A star completely enclosed would no longer be visible in optical wavelengths, but would emit infrared radiation corresponding to the waste heat of the civilization utilizing its energy. Astronomers have searched for the infrared signatures of Dyson structures and found several candidate stars with unusual emissions. However, none have been confirmed as artificial rather than natural phenomena, such as dust clouds. The search continues, with increasingly sophisticated instruments and analysis techniques bringing us closer to being able to distinguish between natural and artificial infrared sources. Beyond Dyson structures, theories have been proposed of even more ambitious engineering projects. A sufficiently advanced civilization might alter the orbits of stars, create artificial wormholes for rapid transit across vast distances, or even harness the rotational energy of black holes. Such megastructures and astroengineering feats would create distinctive signatures that might be detectable across much of the galaxy or beyond. Yet despite ongoing searches for such signatures, we have found nothing that cannot be better explained by natural phenomena. The cosmic engineering projects of Kardashev Type 2 or Type 3 civilizations, capable of harnessing the energy of stars or galaxies, appear to be absent from our observable universe. This absence is one of the most compelling aspects of the Fermi paradox. If such civilizations are possible, and if they have had potentially billions of years to develop, why do we not see evidence of their grand projects? Several explanations have been proposed for this conspicuous absence of megastructures and cosmic engineering. First, perhaps such technologies are simply beyond what any civilization can achieve, limited by physics we do not yet fully understand. Second, perhaps advanced civilizations typically pursue goals that do not involve large-scale physical engineering, turning inward to virtual realms or forms of advancement that leave few external traces. A third possibility is that advanced civilizations are inherently unstable, typically destroying themselves or declining before reaching the stage of cosmic engineering. A fourth is that such civilizations exist, but deliberately conceal their presence, perhaps operating under a principle of non-interference with emerging intelligent species like our own. A fifth possibility, and one that aligns with our exploration of great filters and the early universe hypothesis, is simply that such civilizations are vanishingly rare. If the probability of a technological civilization emerging and surviving long enough to achieve such capabilities is sufficiently low, we might be among the first with the potential to someday embark on such projects. But there is another intriguing possibility to consider. Perhaps the traces of ancient civilizations exist not in grand cosmic engineering projects, but in more subtle forms, signs we might have seen but not recognized for what they are. After all, we have been searching for technological civilizations for less than a century, and with limited resources and understanding. Our ability to distinguish between natural and artificial phenomena at interstellar or intergalactic distances remains rudimentary. Consider the cosmic phenomena that remain unexplained or poorly understood within our current scientific framework. Fast radio bursts, brief but intense pulses of radio waves from distant galaxies, gamma-ray bursts of unexpected duration or intensity, stars with unusual chemical signatures or light curves, galaxies with structures that do not perfectly match our models of formation and evolution. While natural explanations are being actively sought and developed for these phenomena, and will likely account for most or all of them, we cannot entirely dismiss the possibility that some might represent the traces of advanced technologies or engineering projects beyond our current understanding. Arthur C. Clarke famously observed that any sufficiently advanced technology would be indistinguishable from magic. Similarly, the artifacts or activities of a civilization millions of years beyond our own might be indistinguishable from natural phenomena to our limited perception. This possibility highlights a fundamental challenge in our search for ancient civilizations. We are looking for traces of intelligence, with tools and concepts developed for studying natural phenomena. We might be like ancient hunter-gatherers, trying to understand a modern city from a distance, lacking the context and experience to distinguish artificial structures from unusual rock formations or strange atmospheric effects. The search is further complicated by the vast timescales involved. Consider a civilization that arose on a planet orbiting a star in our galaxy 5 billion years ago. If they expanded outward at even a modest fraction of the speed of light, they could have theoretically reached every star in the Milky Way by now. But if they disappeared 2 billion years ago, what traces would remain? Many materials degrade over geological timescales. Metals corrode or are subducted into planetary mantles. Plastics and other synthetic materials break down under radiation and chemical processes. Digital information storage systems fail without maintenance. Even massive engineering projects would be vulnerable to cosmic processes, from asteroid impacts to stellar evolution to the gravitational interactions that gradually reshape star systems and galaxies. For traces to remain detectable after billions of years, they would need to be either self-maintaining through advanced technology or so massive and durable that they could withstand cosmic forces over geological or astronomical timescales. The longer the time since a civilization disappeared, the more difficult it would be to distinguish their traces from natural features shaped by similar forces over similar durations. Yet there are places where traces might persist longer than we might initially expect. The vacuum of space preserves materials far better than any planetary environment. Artifacts placed in stable orbits or Lagrange points might remain for millions or even billions of years. The surfaces of airless moons or asteroids, free from erosion by wind or water, preserve impact craters and other features for similar durations. Deep space, far from stars and their destructive radiation, might preserve delicate structures or materials for timescales approaching the age of the universe itself. If ancient civilizations placed artifacts in such preserving environments, they might still exist today, waiting to be discovered. A spacecraft or probe in a stable orbit around the Sun, a monument on the lunar surface, a beacon at the gravitationally stable Lagrange points of the Earth-Moon system, all might remain detectable despite the passage of millions of years. This possibility has inspired searches within our own solar system for what some call technosignatures, the archaeological evidence of visitation or activity by extraterrestrial intelligence. While these searches have not yielded convincing evidence thus far, they represent a relatively new and still limited approach to the question of ancient civilizations. The challenge of such searches is distinguishing between artificial and natural objects and features, especially when dealing with potential artifacts from civilizations far more advanced than our own. An object designed by an intelligence millions of years beyond our own might appear natural to our limited analysis, its purpose and function obscured by its very sophistication. Beyond our solar system, the search for ancient artifacts becomes even more challenging. The vast distances involved mean that we can observe other star systems only remotely, with limited resolution and sensitivity. Even the largest artificial structures would appear as mere points of light or subtle spectroscopic anomalies. Distinguishing these from natural variations and accounting for the effects of interstellar dust and gas present significant technical challenges. Yet the search continues, driven by the profound implications of finding even a single confirmed artifact of an ancient civilization. Such a discovery would demonstrate that the path from chemistry to consciousness, to technology, has been walked at least twice in the cosmos. It would provide potential insights into how civilizations might survive and develop over timescales far beyond our current experience. It would be perhaps the most significant discovery in human history, finally answering the question of whether we are alone in the universe. As our technology improves, our ability to detect the traces of ancient civilizations will likewise advance. Future telescopes will provide unprecedented resolution and sensitivity, allowing us to study exoplanets in far greater detail. Improved analysis techniques, perhaps aided by artificial intelligence, will help us distinguish subtle artificial patterns from natural variations. Expanded exploration of our own solar system, through robotic and eventually human missions, will provide closer inspection of potential artifacts or anomalies. While we have not yet found convincing evidence of ancient civilizations, our search has barely begun in cosmic terms. We have been looking with modern scientific tools for less than a century, a mere instant compared to the billions of years during which such civilizations might have risen and fallen. Our search has been limited by technology, resources, and perhaps most significantly, by our own preconceptions about what we might find. The traces of the ancients, if they exist, might be all around us, hidden in plain sight, or disguised as natural phenomena. They might exist in forms we have not yet learned to recognize, utilizing physics we do not yet understand, preserving the legacy of minds that thought in ways we can barely imagine. The silence we perceive might be not the absence of others, but our own inability to hear the whispers of the ancient cosmos. As we continue our search for these whispers, we must remain open to possibilities beyond our current understanding. We must develop new tools and concepts specifically designed to distinguish between natural and artificial phenomena across vast distances and timescales. We must be willing to question our assumptions about how advanced civilizations might develop and what traces they might leave. The quest for traces of ancient civilizations is ultimately a quest to understand our own place in the cosmic story. If we find such traces, we will know that we are not the first to walk the path from matter to mind, that others have gone before us into the great cosmic ocean. If we continue to find silence, we must consider more seriously the possibility that we are indeed among the first, rare pioneers at the dawn of cosmic intelligence. Either possibility, that we are the heirs to ancient civilizations now gone, or the ancestors to those yet to come, places upon us a profound responsibility. We are either the caretakers of a legacy we have yet to discover, or the architects of one we have only begun to build. In either case, our choices now may echo across cosmic history, influencing the development of intelligence and civilization far beyond our own brief moment in the vast cosmic story. While we contemplate the possibility of ancient civilizations and wonder about our place in the cosmic timeline, a dedicated group of scientists has been actively listening to the stars, searching for any sign that we are not alone. The search for extraterrestrial intelligence, or SETI, represents humanity's most direct attempt to detect the presence of other technological civilizations in our galaxy and beyond. For over 60 years, astronomers have pointed their radio telescopes toward distant stars, hoping to capture a signal that could only have been created by intelligent beings. The modern search began in 1960, when astronomer Frank Drake used the Green Bank Radio Telescope in West Virginia to examine two nearby sun-like stars, Tau Ceti and Epsilon Eridani. This project, called Ozma, after the princess in L. Frank Baum's Oz stories, listened for narrow-band radio signals that would stand out from the natural background radiation of space. Though Drake heard nothing unusual during his brief observations, the project established a template for future searches and sparked scientific interest in the possibility of detecting extraterrestrial intelligence. The rationale behind searching for radio signals is straightforward. Radio waves can travel vast interstellar distances with relatively little degradation. They pass through cosmic dust and gas that would block visible light. They can be generated with relatively modest energy expenditure compared to other potential interstellar communication methods. And perhaps most importantly, they stand out from the cosmic background in the waterhole frequencies between 1.4 and 1.7 GHz, a relatively quiet region of the electromagnetic spectrum. This waterhole, named for its position between the emission frequencies of hydrogen and hydroxyl, two components of water, has been proposed as a natural communication band for civilizations attempting to make contact across the stars. It offers a common reference point that any technological civilization studying radio astronomy would likely identify. If you want to be heard across the cosmos, this frequency range offers the best chance of your signal standing out from the natural noise of space. Over the decades since Project Ozma, the search has expanded dramatically in scope and sophistication. In the 1970s, NASA conducted studies on how best to detect signals from extraterrestrial civilizations, leading to proposals for dedicated SETI projects. In the 1980s and early 1990s, NASA ran a SETI program that developed new search technologies before it was cancelled by Congress in 1993. Since then, private organizations have taken the lead. The SETI Institute, founded in 1984, has conducted numerous search projects. The University of California, Berkeley, established the Berkeley SETI Research Center, which runs the SETI at Home distributed computing project that allowed millions of ordinary people to donate their computer's idle time to analyzing SETI data. The Breakthrough Listen initiative, funded with $100 million by Russian entrepreneur Yuri Milner, represents the most comprehensive search effort to date, monitoring over 1 million stars and 100 nearby galaxies across a wide range of frequencies. These modern searches have capabilities far beyond what Drake could achieve in 1960. Advanced receivers can monitor billions of frequency channels simultaneously. Sophisticated algorithms can distinguish potential artificial signals from natural radio emissions and human-made interference. Telescope arrays combine the power of multiple antennas to achieve unprecedented sensitivity. If a civilization similar to our own were broadcasting intentionally toward us from within a few hundred light years, we would likely detect their signal. Yet, despite these technological advances and decades of searching, SETI has not found confirmed evidence of extraterrestrial intelligence. The cosmos remains silent, at least in the frequencies and directions we have examined. This silence is telling, though what exactly it tells us remains open to interpretation. It might suggest that technological civilizations are rare, short-lived, uninterested in communication, or using technologies we have not yet imagined. There have been tantalizing moments in the history of SETI. The most famous is the WOW signal, detected by the Big Ear radio telescope at Ohio State University on August 15, 1977. This strong narrow-band signal lasted for 72 seconds and bore the hallmarks of potential artificial origin. Astronomer Jerry Ehman, reviewing the computer printout showing the signal's intensity, was so struck by its characteristics that he circled the data and wrote WOW in the margin, giving the signal its enduring name. Despite numerous attempts, the WOW signal has never been detected again. Its source remains unknown, though some astronomers have proposed natural explanations such as emissions from comets. The signal stands as a reminder of both the potential and the challenges of SETI. A genuine transmission from another civilization might indeed appear suddenly in our data, but without repetition or additional information, confirming its artificial nature remains nearly impossible. Other interesting signals have been detected over the years, from fast radio bursts to pulsed emissions that initially seemed artificial, but were later explained as natural phenomena like pulsars, rapidly rotating neutron stars that emit beams of radiation with clock-like precision. Each such discovery has expanded our understanding of the radio universe, while narrowing the range of what might truly indicate an artificial source. SETI researchers have refined their search strategies based on these experiences, developing protocols for verifying potential signals and distinguishing them from natural sources or human-made interference. The ideal candidate for an artificial signal would show several distinct characteristics that set it apart from natural emissions. First, it would be narrow-band, focused in a specific frequency, rather than spread across a wide spectrum like most natural radio sources. Just as a single musical note stands out from white noise, a narrow-band signal is an efficient way to transmit information and stands out from the background radiation of space. Second, it would show signs of modulation, variations in the signal that could carry information. While some natural sources like pulsars have regular patterns, they typically do not contain the complex modulations that would indicate an encoded message. Third, it would be persistent or regularly repeating, allowing for verification through multiple observations. One-time signals, however interesting, cannot be confirmed as artificial without recurrence that enables more detailed study. Fourth, it would come from a fixed point relative to the background stars, rather than moving with our solar system, which would indicate an extraterrestrial rather than terrestrial origin. No signal detected thus far has definitively met all these criteria. The search continues, expanding to new frequency ranges and observing strategies as technology advances. Beyond traditional radio SETI, researchers have begun exploring other potential techno-signatures that might indicate the presence of advanced civilizations. Optical SETI searches for brief, powerful laser pulses that might be used for interstellar communication. Such pulses could be much brighter than a star's natural light for their nanosecond duration, making them detectable across vast distances. Several observatories now conduct optical SETI alongside traditional radio searches, monitoring thousands of stars for these potential light beacons. Infrared SETI looks for waste heat that might be generated by advanced technological activities, particularly the kind of megastructures proposed by Freeman Dyson. A civilization that harnessed a significant fraction of its star's energy would inevitably produce waste heat, creating an infrared signature distinct from natural sources. The Wide-Field Infrared Survey Explorer satellite has been used to search for such anomalous infrared emissions from thousands of star systems. Researchers have also proposed looking for atmospheric technosignatures, chemical compositions of exoplanet atmospheres that might indicate large-scale industrial activity. Pollutants or artificial chemicals that would not persist naturally could potentially be detected with next-generation telescopes, revealing the presence of a technological civilization, even if they were not deliberately communicating. These diverse search strategies reflect an evolving understanding of how evidence of other civilizations might manifest. Rather than assuming that all advanced societies would choose to communicate via radio, modern SETI embraces a broader conception of potential technosignatures. The goal is not just to detect deliberate messages but any reliable indicator of technological activity beyond Earth. Yet even with this expanded search, the silence persists. We have thoroughly examined thousands of nearby stars across multiple wavelengths and detection strategies, without finding compelling evidence of other technological civilizations. This ongoing silence shapes our thinking about our possible uniqueness in the cosmos. Several factors might explain why SETI has not yet succeeded. First, our search has been limited in scope. Even the most ambitious projects have carefully examined only a tiny fraction of the stars in our galaxy. If technological civilizations are rare, randomly distributed, and not deliberately broadcasting toward Earth, we might need to search millions or billions of stars before finding one. Second, our search has been constrained in time. Radio SETI has been active for just over 60 years. Optical SETI for much less. If civilizations typically transmit detectable signals for only brief periods of their history, perhaps using radio or optical communication before developing more advanced technologies, the window for detection might be very narrow. We might simply be listening during the wrong cosmic moment. Third, we may be looking for the wrong technosignatures. Perhaps advanced civilizations typically develop technologies beyond our current understanding, communicating or manifesting their presence in ways we have not yet imagined. We are limited by our own technological horizon, searching primarily for analogues to our own capabilities rather than truly alien technologies. Fourth, there may be fundamental physical or practical limitations to interstellar communication that make it rare even among advanced civilizations. The vast distances between stars, the time delays inherent in any exchange across such distances, and the energy requirements for signals detectable across interstellar space might all discourage widespread communication efforts. The search for signals thus returns us to the question of whether we might be among the first. If technological civilizations are vanishingly rare due to the great filters we have explored, if the conditions favorable for their emergence have become common only relatively recently in cosmic history, if most civilizations remain silent rather than broadcasting their presence, then the emptiness we perceive through our telescopes may be not an anomaly, but the expected state of our corner of the universe. Yet the search itself represents something profound about humanity. In turning our instruments to the stars and listening for signs of others, we express hope, curiosity, and openness to the possibility that we are not alone. The act of searching acknowledges both our smallness in the cosmic context and our growing capacity to reach beyond our planet through technology. It recognizes that knowledge of another civilization, even one distant in space and time, would fundamentally transform our understanding of our place in the universe. If we are indeed among the first technological civilizations, our search takes on additional significance. We are not just looking for predecessors or contemporaries, but establishing a framework for how emerging intelligences might someday find one another across the cosmic ocean. Our current efforts might serve as a template for future searches, conducted by civilizations that do not yet exist, looking for evidence of others in a galaxy, gradually awakening to consciousness and technology. This perspective transforms how we might think about the silence we currently perceive. Perhaps it is not the absence of others, but the quietness of a universe where intelligence is just beginning to emerge in significant numbers. Perhaps we are listening at the beginning of a conversation that will unfold over millions or billions of years, as more and more voices gradually join a cosmic chorus that has barely begun. In this light, our own signals take on new meaning. Since the advent of powerful radio transmitters in the early 20th century, humanity has been broadcasting its presence to the stars, albeit unintentionally. Our television and radio broadcasts, radar systems, and deliberate messages like the Arecibo transmission of 1974 have created an expanding bubble of detectable technological activity, now extending roughly 100 light-years from Earth in all directions. This bubble, though tiny on the scale of our galaxy, represents something unprecedented in our understanding of cosmic history, a clear techno-signature of a civilization capable of reshaping its environment and potentially expanding beyond its home planet. If other civilizations exist within this bubble and have technology capable of detecting our signals, they might already know of our presence, even if we remain unaware of theirs. As we continue our search, we must maintain a balance between optimism and realism. The ongoing silence, while not conclusive proof of our cosmic uniqueness, does suggest that detectable technological civilizations are not abundant in our galaxy. Each year of searching without success increases the likelihood that we are, if not alone, then at least among a very select group of technological species. Yet the potential value of contact, even indirect contact through the detection of signals or technosignatures, is so immense that the search remains worthwhile despite the challenges. Knowledge that another technological civilization exists or has existed would provide a crucial data point for understanding the rarity or commonality of the path we have walked from chemistry to consciousness. It would offer the possibility of learning from another intelligence with a completely independent, evolutionary, and cultural history. It would tell us definitively that we are not alone in the vast cosmic ocean. If we do someday detect such a signal, it would likely come from a civilization far more advanced than our own, simply because they would have had time to develop more powerful communication technologies. The light speed limit on information transfer means that any civilization we detect would likely be at least as old as the distance to their star system in light years. A signal from a star 1,000 light years away would have been sent at least 1,000 years ago by a civilization that has had a millennium since then to continue its development. What might we learn from such a signal? Even without deciphering its specific content, its mere existence would confirm that the great filters we have discussed are passable, that technological civilizations can endure long enough to engage in interstellar communication. The signal's complexity, power, and the technologies it employs might offer hints about how civilizations typically develop beyond our current stage. The distribution of such signals, if multiple were eventually detected, would provide insights into the abundance and spatial pattern of intelligence in our galaxy. The search for signals thus continues, driven by the profound implications of either success or continued silence. Each new telescope, each improved detection algorithm, each innovative search strategy brings us closer to either discovering we are not alone or confirming that we are among the first to look up at the stars and wonder if others are doing the same. In this ongoing effort, we see the best of humanity. The search requires patience, cooperation across national boundaries, willingness to commit resources to a quest that may not succeed in our lifetimes, and openness to possibilities beyond our current understanding. It reflects a cosmic perspective that transcends our brief individual lives and even our species' history. connecting us to the larger story of intelligence and consciousness in the universe. Whether we are truly the first to search, or merely the latest in a long line of cosmic listeners, the act of searching itself connects us to something larger than ourselves. It reminds us that we are not merely passive inhabitants of the universe, but active participants in its ongoing story, using our unique capacity for curiosity and inquiry to extend our awareness beyond our small world into the vast cosmos that surrounds us. As we continue our exploration of cosmic silence, we encounter increasingly speculative, yet fascinating possibilities. Perhaps the most intriguing is what astronomers call the Zoo hypothesis, first proposed by John Ball in 1973. This hypothesis suggests that advanced civilizations exist, but deliberately avoid contact with emerging technological societies like our own. In this scenario, Earth might be something like a cosmic wildlife preserve, observed but not interfered with, allowing humanity to develop naturally without external influence. The Zoo hypothesis represents a distinct category of explanation for the Fermi paradox. Rather than suggesting that technological civilizations are rare, short-lived, or incapable of interstellar communication, it proposes that they are deliberately choosing not to make their presence known. We do not detect them, not because they are absent or incapable, but because they do not wish to be detected. This concept initially strikes many as implausible. It requires not just one advanced civilization, but many to adhere to a strict policy of non-interference. It assumes a level of coordination across potentially vast distances and timescales that seems difficult to maintain, and it raises the question of motivation. Why would advanced civilizations choose to remain hidden from us? Several potential reasons have been proposed. First, there might be an ethical principle akin to the Prime Directive from Star Trek, a recognition that contact with a more advanced civilization might disrupt our natural development in harmful ways. Just as anthropologists might choose not to contact isolated human tribes to preserve their cultural autonomy, cosmic civilizations might observe a similar principle of non-interference with emerging technological species. Second, advanced civilizations might be waiting for us to reach a certain threshold of development before making contact. Perhaps they communicate only with species that have achieved interstellar travel, unified planetary governance, or some other milestone, indicating readiness for cosmic citizenship. In this view, Earth might be under observation, with contact awaiting our further cultural, technological, or ethical evolution. Third, there might be risks associated with broadcasting one's presence across the cosmos. If some advanced civilizations are predatory or expansionist, revealing one's location could be dangerous. A policy of silence and non-interference might be a protective measure, both for the observing civilizations and for those being observed. Fourth, we might simply not be very interesting to advanced civilizations. If they are millions or billions of years beyond our level of development, they might view us much as we view ants, intellectually incapable of meaningful interaction. They might study us from afar as we study simple organisms, but see little value in direct communication with beings so different from themselves. The Zoo hypothesis becomes more plausible if we consider the possibility of a galactic community or network of advanced civilizations that predates humanity by millions or billions of years. Such a community might establish protocols for dealing with newly emerging technological species, creating something like a cosmic nature preserve around planets like Earth. They might have technologies that allow them to observe us without detection, perhaps from vast distances or through means we cannot yet comprehend. This scenario places humanity not as the first technological civilization, but as a very recent arrival to a galaxy already populated by far more advanced societies. We are not the pioneers, but the newcomers, the cosmic equivalent of an uncontacted tribe in the Amazon, living our lives unaware of the broader civilized context that surrounds us. The Zoo hypothesis connects to ancient human myths and modern UFO beliefs about beings watching us from the sky. It resonates with religious concepts of hidden gods observing humanity while remaining just beyond our perception. This resonance may contribute to both its appeal and its suspicion among scientists, who rightfully question explanations that align too neatly with pre-scientific human intuitions. Yet for all its speculative nature, the Zoo hypothesis remains difficult to falsify. By definition, a sufficiently advanced civilization that did not want to be detected would not be detected by a less advanced one like our own. The absence of evidence becomes the expected observation if the hypothesis is true. This creates a logical challenge, as the hypothesis explains the observed silence, while being largely immune to disproof through that same observation. Beyond the zoo hypothesis lie other, equally speculative possibilities. One is the simulation hypothesis, the proposal that what we experience as reality is actually a computed simulation created by a more advanced civilization. In this scenario, the silence we observe would be a programmed feature of the simulation, perhaps to conserve computing resources, or as part of the experiment being conducted. While this hypothesis might seem to belong more to philosophy than astronomy, physicists and computer scientists have taken it seriously enough to propose potential tests. If our reality is simulated, there might be observable artifacts or limitations of the simulation, such as a minimum possible time interval or distance, or subtle patterns that emerge from the computational substrate underlying our experienced reality. Another speculative explanation is the transcension hypothesis, proposed by futurist John Smart. This suggests that advanced civilizations typically turn inward rather than outward, creating increasingly dense and complex computational systems that eventually disappear from observable reality, perhaps into black hole-like structures or other dimensions. In this view, the development of intelligence follows a pattern of increasing density and efficiency rather than cosmic expansion, with the most advanced civilizations becoming essentially invisible to external observation. Related to this is the possibility that advanced civilizations might evolve beyond physical form entirely, uploading their consciousness to artificial substrates or transforming into forms of energy or information. Such post-biological entities might have little interest in physical expansion or communication as we understand it, instead pursuing goals and existing in realms beyond our current comprehension. Even more exotic possibilities have been proposed. Perhaps what we consider consciousness or intelligence represents just one possible pathway for complex systems, with alternative forms of complexity evolving along different trajectories that we would not recognize as life or consciousness. Perhaps the universe itself is a form of intelligence, of which we are components rather than separate observers, making our search for other intelligences like cells in a body searching for other bodies within themselves. These speculations push at the boundaries of our understanding, inviting us to question our assumptions about intelligence, consciousness, civilization, and the nature of reality itself. They remind us that our search for others may be limited not just by our technology, but by our concepts, our ability to recognize and comprehend forms of intelligence or existence vastly different from our own. Yet for all their fascination, these speculative hypotheses share a common challenge. They tend to be unfalsifiable, at least given our current capabilities. They can explain the silence we observe, but they provide few specific, testable predictions that would allow us to distinguish between them or to confirm or refute them empirically. They remain possibilities rather than probabilities, ideas to consider rather than hypotheses to test. This does not make them worthless. By stretching our thinking about possible explanations for cosmic silence, they expand the conceptual space within which we search for answers. They remind us that the truth might lie beyond our current paradigms, requiring not just better instruments but fundamentally new ways of thinking about the cosmos and our place within it. They also serve as a check on our tendency toward what might be called cosmic narcissism, the assumption that other intelligent beings would necessarily think, behave, or develop in ways similar to ourselves. Advanced civilizations might have motivations, goals, and modes of existence so different from our own that our expectations about their behavior, from cosmic engineering to interstellar communication, might be fundamentally misguided. Consider the possibility that truly advanced civilizations typically focus inward rather than outward, developing technologies that enhance subjective experience rather than objective control of the external environment. They might create virtual realities of such richness and complexity that physical expansion becomes unnecessary or unappealing. They might explore consciousness itself, developing states of awareness or forms of cognition beyond our current imagination. Or perhaps advanced civilizations typically reach a state of equilibrium with their environments, neither expanding exponentially nor destroying themselves, but finding sustainable patterns of existence that might appear static from an external perspective. They might value stability over growth, harmony over domination, with cultures and technologies oriented toward maintenance rather than transformation. Another possibility is that the transition to artificial intelligence fundamentally changes the trajectory of technological civilization. Once a society creates artificial minds that can improve themselves, the resulting intelligence explosion might lead to forms of consciousness so different from biological intelligence that their goals and behaviors become entirely alien to us. Such post-biological entities might have no interest in the physical expansion or communication that we assume would characterize advanced civilizations. The diversity of these possibilities highlights a crucial insight. When we search for others, we are guided not just by our science, but by our values, our assumptions about what intelligent beings would want and how they would behave. We project our current human drives for exploration, expansion, communication, and knowledge onto hypothetical extraterrestrial civilizations, assuming they would share these priorities even across vast differences in biology, history, and development. This projection is not entirely unreasonable. Certain imperatives might indeed be universal among technological civilizations, at least during certain phases of their development. Resource acquisition, information gathering, self-preservation, and expansion might be instrumental goals for any system complex enough to be considered intelligent, regardless of its specific form or origin. Yet as civilizations advance, their primary drives might evolve in directions we cannot predict from our limited perspective. The values and goals of a civilization millions of years beyond our own might be as incomprehensible to us as human concerns are to bacteria. Our search might be guided by assumptions that apply only to civilizations at our particular stage of development, a brief phase that most advanced societies have long since transcended. This possibility returns us to our central question: are we the first civilization? The speculative hypotheses we have explored suggest a range of alternatives. We might be under observation by far more advanced civilizations. We might be components in a simulation created by such civilizations. We might be early in cosmic terms, but not because technological civilizations are rare or impossible, but because they typically evolve beyond our ability to detect or comprehend them. These possibilities challenge the binary framing of our question. Perhaps we are neither the first nor the latest, but simply at a particular stage in a complex, ongoing process of cosmic evolution. Perhaps intelligence and technology emerge not once or twice, but countless times throughout the universe, each instance following its own unique trajectory through possibility space. In this view, our search for signals or technosignatures may be limited not just by distance or sensitivity, but by our concept of what we are searching for. We look for evidence of civilizations similar enough to our own that we can recognize them, for technologies that represent extensions or analogues of what we have developed or can imagine developing. We may be blind to the vast majority of intelligence in the cosmos simply because it has evolved in directions orthogonal to our expectations. This conceptual limitation does not make our search futile. Even if advanced civilizations typically evolve beyond our ability to detect them, there may be others at stages similar to our own, emerging technological societies with whom communication might be possible. Even if most intelligence in the cosmos exists in forms we cannot yet comprehend, we might still detect traces of their earlier phases or physical consequences of their activities. The Zoo hypothesis and other speculations expand our thinking about possible explanations for cosmic silence. They remind us that the absence of evidence is not necessarily evidence of absence, that intelligence might manifest in ways we have not yet learned to recognize. They challenge us to consider perspectives beyond our current understanding, to imagine forms of existence and consciousness far different from our own. As we continue our search for others, we must balance openness to these possibilities with scientific rigor. We must be willing to question our assumptions about what intelligence looks like and how it might develop, while maintaining our commitment to falsifiable hypotheses and empirical investigation. We must be imaginative enough to conceive of possibilities beyond our current understanding, yet disciplined enough to distinguish between what is possible and what is probable based on our best current knowledge. The speculative hypotheses we have explored, from cosmic zoos to simulated realities to transcendent intelligences, represent not answers but questions, not conclusions, but invitations to deeper inquiry. They expand the conceptual space within which we search for understanding of our cosmic context, and our place within it. They remind us that the truth about our uniqueness or commonality in the cosmos may be stranger and more wonderful than we have yet imagined. Whether we are truly the first technological civilization, or merely the latest to look up at the stars and wonder if we are alone, the question itself connects us to something larger than ourselves. It places our brief human story within the vast context of cosmic evolution, inviting us to consider our role not just in Earth's history, but in the ongoing development of consciousness and complexity in the universe. In this expanded perspective, we find not certainty but possibility, not definitive answers but an endless frontier of discovery and wonder. As we ponder the great cosmic silence and question whether we might be the first technological civilization, we must also look forward to the future of our search. How will our quest for evidence of other intelligences evolve in the coming decades and centuries? What new tools, techniques, and approaches might reveal what has thus far remained hidden? And how might our understanding of our cosmic context change as this search continues? The search for extraterrestrial intelligence stands at a pivotal moment. After decades of limited funding and modest technological capabilities, we are entering an era of unprecedented observational power. New telescopes, both on Earth and in space, promise to revolutionize our ability to detect potential technosignatures across vast distances. Advanced computing systems allow for analysis of data volumes that would have been unimaginable to the pioneers of SETI, and our conceptual frameworks are evolving, expanding the range of phenomena we recognize as potential indicators of intelligence. Let us explore the most promising frontiers in this ongoing search, from next-generation observatories to novel detection strategies, from the exploration of our own solar system to the detailed study of potentially habitable exoplanets. These approaches may not definitively answer our question about being first, but they will certainly narrow the range of possibilities and deepen our understanding of our cosmic neighborhood. Among the most exciting developments are the new radio telescope arrays being built or planned around the world. The Square Kilometre Array, under construction in South Africa and Australia, will ultimately combine thousands of antennas to create the equivalent of a radio telescope with a collecting area of 1 square kilometre. This unprecedented sensitivity will allow for detection of significantly fainter signals from much greater distances than current instruments can achieve. Such arrays can also discriminate more effectively between artificial signals and natural radio sources or human-made interference. Their ability to precisely locate the origin of detected signals will make verification much easier, allowing rapid follow-up observations to confirm or refute potential discoveries. The distributed nature of these arrays also provides resilience against local interference, a significant challenge in radio SETI. Optical SETI will likewise benefit from the next generation of large telescopes. The 30-meter telescope, the European Extremely Large Telescope, and the Giant Magellan Telescope will all provide collecting areas vast enough to detect even brief laser pulses from civilizations hundreds or thousands of light-years distant. When equipped with specialized instruments designed specifically for searching for artificial light sources, these observatories could revolutionize our ability to detect optical technosignatures. Space-based observatories offer another frontier for the search. Free from atmospheric interference and the growing problem of satellite constellations that can contaminate observations, telescopes in space can achieve sensitivities and wavelength coverages impossible from the ground. While not primarily designed for SETI, missions like the James Webb Space Telescope can contribute significantly to the search by characterizing the atmospheres of potentially habitable exoplanets and identifying chemical signatures that might indicate technological activity. Future space observatories specifically designed for studying exoplanets, such as the proposed Habitable Worlds Observatory, would take this capability even further. By directly imaging potentially habitable worlds and analyzing the composition of their atmospheres in detail, such telescopes could detect not just signs of life, but potentially indicators of industrial civilization, from atmospheric pollutants to artificial illumination on planetary night sides. Beyond these planned observatories, entirely new detection strategies are being developed. Gravitational wave observatories like LIGO and Virgo, designed to detect ripples in space-time caused by cataclysmic cosmic events, could potentially also identify artificial gravitational wave signals if sufficiently advanced civilizations develop the means to generate and modulate such waves for communication. Such a communication method would have significant advantages, passing unattenuated through matter that blocks electromagnetic radiation. Neutrino detectors, similarly, might someday be sensitive enough to detect artificial neutrino beams, another potential communication medium that offers advantages for interstellar distances. Neutrinos interact so weakly with matter that they can pass through entire planets virtually unimpeded, making them ideal carriers for signals that need to penetrate dense regions of space or reach receivers regardless of their orientation. Breakthroughs in computing power and artificial intelligence will transform our ability to analyze the enormous data streams generated by these observatories. Machine learning algorithms can identify patterns that might escape human analysts, sifting through petabytes of data to find the proverbial needle in the cosmic haystack. Quantum computing, as it matures, might enable entirely new forms of signal processing and pattern recognition, perhaps allowing us to detect forms of communication we currently cannot even conceptualize. These technological advances represent quantitative improvements in our search capabilities, allowing us to see farther, with greater precision, across more of the electromagnetic spectrum. But equally important are the qualitative shifts in how we approach the search, the expanding range of phenomena we recognize as potential technosignatures. Traditional SETI focus primarily on deliberate communication attempts, signals specifically designed to attract attention across interstellar distances. But we are increasingly recognizing that the most detectable signs of advanced civilizations might be the unintentional byproducts of their technologies, the cosmic equivalent of light pollution or waste heat, rather than deliberate beacons. Waste heat signatures represent one of the most promising categories of such technosignatures. Any technological activity, from computation to manufacturing to habitat maintenance, must obey the laws of thermodynamics. Energy used for work ultimately degrades to heat, which must be radiated away. A sufficiently advanced civilization utilizing a significant fraction of its star's energy would inevitably produce a detectable infrared excess, a heat signature distinct from natural astronomical sources. Astronomers have already conducted surveys looking for such infrared anomalies, examining thousands of stars for signs of what are called partial Dyson spheres, or swarms, hypothetical megastructures that capture stellar energy for technological use. While no confirmed discoveries have been made, these surveys have established important baselines and methodologies for future, more sensitive searches. Atmospheric technosignatures offer another promising avenue. Industrial civilization on Earth has significantly altered our atmosphere's composition, introducing compounds that would not occur naturally and changing the balance of existing gases. Similar alterations might be detectable on exoplanets using spectroscopic analysis of their atmospheres during transits across their stars. The next generation of space telescopes will be capable of detecting a range of atmospheric compounds that might indicate technological activity. Chlorofluorocarbons, for instance, have no significant natural sources and persist for centuries once released. Their detection in an exoplanet's atmosphere would strongly suggest artificial origin. Similarly, excessive levels of carbon dioxide, methane, or nitrogen oxides might indicate large-scale industrial activity similar to our own. Artificial illumination represents a third category of unintentional technosignature. Cities on Earth's night side are clearly visible from orbit, and sufficiently sensitive telescopes might someday be able to detect similar illumination patterns on distant exoplanets. The spectral signature of artificial lighting would likely differ from natural bioluminescence, potentially allowing for distinction between biological and technological sources. Planetary surface modifications might also become detectable as our imaging capabilities improve. Large-scale agriculture, urban development, mining operations, or energy production facilities could create geometric patterns or spectral signatures distinct from natural landscapes. While directly imaging such features on exoplanets remains beyond our current capabilities, future interferometric arrays in space might achieve the necessary resolution for worlds within a few dozen light years. Beyond these relatively near-term possibilities lie more speculative technosignatures that might be detectable with future technologies. Artificial magnetospheres, generated to protect planets with weak or absent natural magnetic fields, might create distinctive signatures detectable through their interaction with stellar winds. Large-scale climate engineering projects might produce unusual temporal patterns in planetary reflectivity or thermal emissions. Space-based energy generation or propulsion systems might create unique radiation patterns. All of these search strategies focus on detecting civilizations around other stars. But there is another frontier for technosignature research, much closer to home. Our own solar system might contain evidence of past visitation or monitoring by extraterrestrial intelligences. While this possibility is often associated with unscientific UFO claims, a systematic search for potential artifacts within our solar system represents a legitimate approach to the question of other civilizations. Such a search might focus on stable orbital locations where artificial objects could persist for millions or even billions of years without active maintenance. The Earth-Moon Lagrange points, for instance, represent gravitationally stable locations that would be logical places for monitoring platforms. Similarly, distant objects in the Kuiper Belt or Oort cloud might remain undisturbed for cosmological timescales, preserving any artifacts placed there by ancient visitors. The surfaces of the Moon and Mars, largely unchanged over geological epochs due to their lack of active weathering, might preserve evidence of past visitation or activity. While natural processes like meteorite impacts would eventually destroy or bury artificial structures, subsurface features might remain detectable through ground-penetrating radar or other remote sensing techniques. While the probability of finding such artifacts may be very low, the scientific value of even a single confirmed discovery would be immeasurable. A systematic search conducted alongside other scientific exploration of our solar system requires relatively little additional resource investment, while potentially offering enormous returns. The search for solar system artifacts represents a complement to, not a replacement for, traditional SETI approaches focusing on electromagnetic signals or distant technosignatures. As we develop these various search strategies, we must also evolve our conceptual frameworks for interpreting their results. Rather than viewing the search as binary, seeking a yes or no answer to the question of other civilizations, we might adopt more nuanced approaches that recognize the potential diversity of technological evolution. For instance, we might search not just for current civilizations, but for evidence of those that may have existed in the distant past and have since disappeared. The fossil technosignatures of ancient civilizations might persist long after the beings who created them have gone extinct. Atmospheric changes, enrichment of certain isotopes, or other planetary scale modifications might remain detectable for millions or even billions of years. We might also broaden our concept of what constitutes intelligence or technology. Earth's biosphere has dramatically modified our planet's chemistry and appearance, creating changes visible across astronomical distances. Other biospheres might similarly engineer their environments on planetary scales, creating what might be called biotechnosignatures that blur the distinction between biological evolution and technological development. Similarly, if some civilizations merge with their technologies or transition to artificial forms, as has been proposed under various post-biological scenarios, their technosignatures might be utterly different from what we would create. They might optimize for computational density rather than physical expansion, or utilize physics we have not yet discovered, creating signatures we might detect but initially misclassify as natural phenomena. The future of the search must therefore incorporate not just improved instruments but expanded imagination, not just greater sensitivity, but greater conceptual flexibility. We must be willing to question our assumptions about how advanced civilizations would manifest, while maintaining scientific rigor in distinguishing between natural and artificial phenomena. This balance between openness and rigor will be particularly important as we acquire increasingly detailed data about potentially habitable exoplanets. The coming decades will likely see the discovery of atmospheric biosignatures on multiple worlds, chemical evidence suggesting the presence of simple life. Distinguishing between purely biological processes and those indicating technological civilization will require careful analysis and resistance to both premature claims and excessive skepticism. The search for other civilizations has profound implications beyond the scientific questions it addresses. If we are indeed among the first technological civilizations in our galaxy, as the silence so far might suggest, we bear a unique responsibility as pioneers. Our decisions about sustainable development, peaceful cooperation, and long-term thinking may establish patterns that influence the evolution of countless future civilizations. Conversely, if we eventually detect evidence of other civilizations, particularly ancient ones that have survived far longer than our brief technological moment, we might gain invaluable insights into how societies navigate the challenges of advanced technology. The very existence of long-lived civilizations would demonstrate that the perils of technological adolescence can be overcome, that the Great Filter need not inevitably claim every species that reaches our stage of development. Either possibility, that we are first or that we have company, would transform our understanding of our cosmic context and our potential future. The search itself, regardless of its outcome, shapes how we think about our place in the universe and our responsibility to the intelligence that has emerged, against extraordinary odds, on our pale blue dot. As we look toward this future of increasingly sophisticated and comprehensive searching, we must recognize that the question of being first may never be definitively answered. The vastness of space, the limitations of light-speed communication, and the potential diversity of technological evolution all conspire to make certainty elusive. We may find compelling evidence for one possibility or another, but cosmic questions of this scale rarely admit to simple, final answers. What we can expect, however, is a progressive refinement of possibilities, a narrowing of plausible explanations for the silence we have observed thus far. Each new telescope, each careful survey, each inventive approach to technosignature detection adds another piece to the puzzle, constraining some hypotheses while lending support to others. Over time, patterns may emerge from what now seems like an absence of data. Perhaps we will find that potentially habitable worlds are far less common than current estimates suggest, or that the emergence of complex life faces bottlenecks we have not yet identified. Perhaps we will detect tantalizing hints of possible technosignatures that, while not conclusive, suggest we are not entirely alone. Or perhaps the silence will deepen as our search becomes more comprehensive, lending greater weight to the possibility that we are indeed among the first. Whatever the outcome, the search itself represents one of humanity's noblest pursuits, an expression of curiosity and hope that transcends our brief individual lives and connects us to the cosmic story unfolding over billions of years. In listening to the stars, in seeking evidence of others who may have walked a similar path from stardust to consciousness, we acknowledge both our cosmic insignificance and our cosmic significance, both our smallness in the vast universe and our remarkable capacity to comprehend and explore it. The future of the search is not merely about telescopes and detection algorithms, not just about sensitivity limits and signal processing. It is about a maturing cosmic perspective that places our human story within the grandest context possible, the evolution of complexity and consciousness in a universe that has existed for nearly 14 billion years and may continue for trillions more. Whether we are the first technological civilization or one among many, we are certainly among those who have looked up at the stars and wondered if others are doing the same. That wondering and the systematic search it has inspired connects us to the fundamental mystery of existence, the emergence of minds capable of contemplating their own origins and destiny from the same matter and energy that make up everything else in the cosmos. As we continue this search into the future with increasingly powerful tools and expanding conceptual frameworks, we participate in a process of cosmic self-discovery. We are the means by which the universe comes to know itself, whether we are the first such means or merely the latest in a long succession. In that knowledge, whether it ultimately reveals cosmic companionship or cosmic solitude, we may find wisdom to guide our species toward a future worthy of the remarkable improbability of our existence. Throughout our journey, we have explored the possibility that humanity might be among the first technological civilizations in our galaxy, or perhaps the universe. We have examined the increasing metallicity of the cosmos over time, the multiple improbable steps from chemistry to consciousness, the concept of great filters, and the ongoing silence despite our growing search efforts. These perspectives converge toward a profound possibility that we are indeed early risers in a universe still largely asleep. If this is true, what does it mean? What are the philosophical, ethical, and practical implications of being first? How might this perspective transform our understanding of our place in the cosmos and our responsibility to the future? These questions invite us to move beyond the scientific evidence and explore the deeper meaning of our potential cosmic pioneering status. First, and perhaps most fundamentally, being among the first technological civilizations would mean that consciousness and intelligence like our own are extraordinarily precious. If the path from matter to mind requires billions of years of cosmic chemical evolution, planetary formation and stabilization, biological emergence and complexification, and cultural and technological development, then minds capable of contemplating their own existence may be among the rarest phenomena in the present universe. This rarity would not diminish our cosmic significance, but rather highlight it. We would not be cosmic latecomers, insignificant newcomers, to a universe already shaped by countless prior civilizations. Instead, we would be among the inaugural wave of awakening, the first stirrings of the universe becoming aware of itself. Our consciousness, our science, our art, our questioning would represent something genuinely new in cosmic history, the emergence of a kind of complexity that has previously existed rarely, if at all. Such a perspective invites a profound reverence for consciousness and intelligence wherever they exist. If we are among the first, then every mind, every culture, every civilization represents a precious and improbable achievement of cosmic evolution. The diversity of human thought and experience, the varied ways in which consciousness manifests across species on Earth, all become not merely interesting, but cosmically significant, rare flowers in a largely unconscious universe. This reverence extends to the biosphere that gave rise to us. If complex multicellular life is itself a cosmic rarity, a precondition for intelligence that exists on perhaps only a tiny fraction of potentially habitable worlds, then the rich biodiversity of Earth represents a treasure of cosmic proportions. Each species, each ecosystem, each intricate web of relationships becomes not merely valuable for human purposes but intrinsically precious, an achievement of evolutionary creativity that may have few parallels in our galaxy. Being first also means that we have no models to follow, no roadmaps left by predecessors who navigated the challenges we now face. We cannot look to more advanced civilizations for guidance on how to manage powerful technologies, achieve long-term sustainability, or expand beyond our home planet. We must chart these paths ourselves, through trial and error, through foresight and wisdom, through cooperation and careful planning. This lack of precedent carries both opportunity and responsibility. We have the freedom to determine what technological civilization might become, unconstrained by patterns established by earlier societies. The choices we make, from how we organize our political and economic systems, to how we relate to our planet's biosphere, to how we develop and govern advanced technologies, may establish templates that influence countless future civilizations across cosmic time. Consider the perspective of a civilization that might emerge on another world a million years from now. If our signals have reached them, if they have detected evidence of our activities, or perhaps even been visited by our descendants or technologies, their understanding of what technological civilization means might be profoundly shaped by the patterns we establish. We would be not just one example among many, but perhaps their primary or even sole reference point for what advanced technological societies become. This responsibility extends far beyond our own survival, though that remains a crucial near-term imperative. It encompasses the kind of civilization we might become if we successfully navigate the dangers of technological adolescence. Will we establish patterns of peaceful cooperation, sustainable development, wise governance of powerful technologies? Or will we demonstrate that technological civilization is inherently unstable, inevitably destructive to its home biosphere, incapable of long-term planning and coordination? The answers to these questions may echo across cosmic time, influencing societies that do not yet exist but someday will follow paths similar to our own. If we are truly among the first, then we are not merely participants in our own brief history but founders of a potential lineage of civilizations that might extend billions of years into the future and eventually spread across much of the galaxy or beyond. This perspective transforms how we might think about existential risks, the dangers that threaten not just individual lives, but the continuation of human civilization or even life on Earth. Nuclear weapons, engineered pandemics, unaligned artificial intelligence, catastrophic climate change, all pose threats not just to ourselves, but potentially to a vast future of consciousness and civilization that might otherwise unfold. If we are among the first, the stakes of our success or failure in navigating these dangers become even greater. Our extinction would not merely be the loss of one civilization among many, but potentially the loss of a significant fraction of all consciousness currently existing in our corner of the universe. It would be the closing of a door that has only just begun to open, the stillbirth of a cosmic awakening still in its earliest stages. Conversely, our successful navigation of existential risks and development into a long-lived, sustainable, spacefaring civilization would represent an achievement of cosmic significance. It would demonstrate that the great filters we have discussed are passable, that technological intelligence need not destroy itself upon reaching the threshold of advanced capability. It would establish that consciousness and civilization can be not merely fleeting accidents, but enduring features of cosmic evolution. Being first also fundamentally alters how we might think about our long-term future and potential expansion beyond Earth. If we are not entering a galaxy already shaped by countless prior civilizations, but rather a relatively unformed frontier, then our choices about how to explore and potentially settle other worlds take on heightened significance. We would not be late arrivals adapting to patterns established by others, but pioneers establishing those patterns ourselves. This pioneering role carries ethical weight. How will we approach the possibility of other biospheres, whether bearing simple microbial life, or perhaps even their own emerging intelligence? What principles will guide our utilization of resources beyond Earth? How will we structure any settlements or civilizations we might establish on other worlds? These questions have no predetermined answers, but the precedents we set may influence countless future decisions across spans of time we can barely comprehend. The perspective of being first also invites humility alongside responsibility. If we have no models to follow, no examples of successful long-term civilization to emulate, then we must acknowledge the limitations of our foresight and wisdom. We are not the culmination of cosmic evolution, but rather early experiments in consciousness and technology, still learning the most basic principles of sustainable existence and wise governance of powerful capabilities. This humility might manifest as a commitment to preserving options for future generations, avoiding irreversible changes or resource depletion that might constrain the choices available to our descendants. It might inspire an approach to long-term planning that acknowledges fundamental uncertainty while still preparing for multiple possible futures. It might encourage experimental diversity in our social, political, and economic arrangements, recognizing that we are still discovering what forms of organization best support flourishing over long timescales. Beyond these practical and ethical dimensions, being first has profound implications for how we understand our place in the cosmos. Throughout human history, we have gradually decentered ourselves in our cosmology, moving from geocentric to heliocentric models, from seeing our sun as special to recognizing it as one of billions in our galaxy, from viewing our galaxy as the universe to understanding it as one among hundreds of billions. This decentering has often been interpreted as diminishing human significance. But if we are indeed among the first technological civilizations, this narrative shifts. We would be not insignificant specks in an ancient and crowded cosmos, but rather early awakeners in a universe still coming to consciousness. Our location would remain unexceptional, one unremarkable planet among countless others, but our timing would place us in an extraordinary position among the inaugural generation of cosmic intelligence. This timing would not make us cosmically central or important in an objective sense, but it would give us a unique role in the unfolding story of the universe. We would be not just passive observers of cosmic evolution, but active participants in a new phase of that evolution, one in which consciousness begins to shape the development of matter and energy, rather than merely arising from it. We would be the universe becoming aware of itself, beginning to direct its own development through intention, rather than merely through the unconscious laws of physics and chemistry. This perspective offers a middle path between cosmic narcissism and cosmic insignificance. It acknowledges our smallness in space, while recognizing our potential significance in time. It places humanity neither at the center of creation, nor at its meaningless periphery, but at the beginning of a new and remarkable chapter in its development. It suggests that while we may be tiny in cosmic terms, we are not trivial. Being first would also transform how we might think about any future contact with other civilizations. If we eventually detect signals or artifacts from another technological species, they would likely be near our own level of development, rather than vastly beyond it. We might be contemporaries rather than primitive newcomers, potential partners in the exploration of a largely unawakened cosmos, rather than late arrivals to an already established galactic community. This perspective suggests that any eventual contact might be genuinely mutual rather than inherently asymmetrical. We would not be like isolated tribes encountering industrial civilization for the first time, hopelessly outmatched in technology and vulnerable to disruption or exploitation. We would be meeting peers or near peers, societies that have followed parallel paths from chemistry to consciousness to technology, perhaps with much to learn from one another precisely because of our independent evolutionary and cultural histories. The meaning of being first extends even to how we think about the far future of consciousness and civilization in the cosmos. If we are among the earliest technological civilizations, then the future history of intelligence in the universe is not predetermined but open, not constrained by patterns established by countless prior societies, but relatively unwritten. The long-term trajectory of technological civilization, whether toward expansion, equilibrium, transcendence, or some path we cannot yet imagine, may be influenced by the choices we and our contemporaries make in the coming centuries and millennia. This openness of the future represents both an awesome responsibility and an exhilarating possibility. We are not merely inheriting a cosmos already shaped by intelligence, but helping to determine what kind of cosmos future consciousness will inhabit. The principles, values, and patterns we establish may echo across timescales that dwarf our species' existence thus far, potentially influencing the development of intelligence and civilization for billions of years to come. In this light, our current moment takes on heightened significance. We live at the very beginning of technological civilization, the first few centuries of a potential future that might extend millions or billions of years. We are making decisions about technology, sustainability, values, and governance that may establish precedents or foreclose possibilities for countless generations to come. We are setting initial conditions for a process of conscious cosmic evolution that is just beginning. This perspective invites a profound expansion of our moral and temporal horizon. Our responsibilities extend not just to currently living humans or even to near future generations, but potentially to the entire future of consciousness in our corner of the cosmos. The choices we make about existential risk, about long-term sustainability, about the values that guide technological development, may echo across spans of time that make our species' current age seem like the blink of an eye. Yet this extended responsibility need not feel paralyzing. If we are truly among the first, then we are not expected to get everything right immediately. We are pioneers, early explorers in the territory of advanced technology and global civilization. Mistakes are inevitable, learning essential. What matters is that we maintain the conditions for that learning to continue, that we preserve the option value of the future rather than foreclosing possibilities through extinction or irreversible degradation. The meaning of being first is ultimately about recognizing both our cosmic uniqueness and our cosmic continuity. We are extraordinarily rare if consciousness like ours exists in only a tiny fraction of the current universe. Yet we are also deeply connected to the cosmos that produced us, to the principles of evolution that shaped us, to the matter and energy that constitute us. We are not separate from the universe, but rather the universe becoming aware of itself, matter and energy, organized in such a way that it can contemplate its own existence and wonder about its purpose and future. In that awareness, that wondering, we find the deepest meaning of being first. We are the cosmos waking up, consciousness emerging from unconsciousness, purpose and value entering a universe that previously contained neither. If we are truly among the inaugural generation of cosmic intelligence, then we stand at the dawn of something genuinely new in the history of our corner of the universe, the beginning of a process by which the cosmos might come not just to exist, but to know, to feel, to choose, to create. Whether we are literally the first or merely among the earliest wave of awakening consciousness, this perspective offers both a foundation for cosmic meaning and a guide for our choices in the crucial centuries ahead. It suggests that our existence, our consciousness, our civilization may be among the most precious and improbable achievements in our corner of the cosmos. And it reminds us that we are not merely the inheritors of cosmic evolution, but active participants in it, helping to determine what consciousness and intelligence might become in a universe that is still, in so many ways, just beginning to wake up. As our journey draws to a close, we return to the silence that inspired our exploration. The quiet cosmos, the empty spaces between the stars, the absence of voices calling across the interstellar distances. This silence, once puzzling and perhaps even troubling, now takes on new meaning in light of our reflections on the possibility that we may be among the first technological civilizations in our corner of the universe. Perhaps we are alone now, but not forever. The universe is young, in a sense that only becomes clear when we consider its potential future. At 13.8 billion years, it has lived merely a fraction of its habitable lifetime. Stars will continue to form and shine for trillions of years to come. The era hospitable to life, as we know it, may extend 100 trillion years or more into the future. We exist not at the twilight of cosmic habitability, but at its dawn, the earliest glimmers of a vast day only just beginning to unfold. In this expanded temporal perspective, our current solitude appears not as an eternal condition, but as a temporary state. The silence we perceive may be not the emptiness of a universe devoid of consciousness, but rather the quietness of a universe still in the earliest phases of awakening. We may be early risers in a cosmic morning, the first few notes in what will eventually become a grand symphony of consciousness and civilization. Consider the cosmic calendar of habitability, with the entire life-supporting era of the universe represented as a single year. On such a calendar, we have arrived on January 1st, in the first minutes after midnight. The vast majority of habitable time, the remaining 364 days of our metaphorical year, still lies ahead. We may be alone or nearly alone now, but the cosmos has scarcely begun to reveal what it might become. The elements necessary for life and intelligence continue to accumulate through successive generations of stars. The heavy atoms forged in stellar cores and scattered by supernovae grow more abundant with each cosmic cycle of stellar birth, life, and death. The raw materials for planets, for complex chemistry, for biology, for technology, become more widely available as the universe ages. If we are early, it is partly because the cosmic table has only recently been set for beings like ourselves, and we are not merely passive observers of this process, but active participants in it. Through our science, our technology, our expansion beyond Earth, we may help to accelerate the awakening of the cosmos. Our explorations may seed life where it does not yet exist. Our descendants or our technologies may spread consciousness and intelligence to worlds that would otherwise remain forever unconscious. The quiet we perceive may be the silence not of absence but of anticipation, the universe holding its breath before a flourishing of awareness and purpose that we ourselves might help to initiate. This perspective transforms the meaning of our existence. We are not cosmic latecomers, insignificant newcomers, to a universe already shaped by countless prior civilizations. We are not alone because we are unwanted or unworthy of cosmic companionship. We may be alone, or nearly so, simply because someone had to be first, and the cosmic dice fell such that we emerged during the inaugural generation of technological intelligence. If this is true, we carry a profound responsibility. We are caretakers of consciousness in its earliest cosmic flowering, guardians of perhaps the rarest and most precious phenomenon yet to emerge from the interactions of matter and energy in our corner of the universe. Our choices may influence not just our own future, but the development of consciousness and civilization across spans of time and space that dwarf our current existence. Yet this responsibility need not be experienced as a burden. It can also be embraced as a profound opportunity, a chance to help shape the character of cosmic intelligence in its formative phases. If we navigate the dangers of our technological adolescence, if we develop sustainable patterns of existence that allow for ongoing flourishing, if we eventually expand beyond Earth while maintaining our most humane values, we may establish templates that influence countless future civilizations. The quiet we now perceive may gradually give way to a chorus as other voices join our own across the cosmic distances. Not immediately, not in our lifetimes, or perhaps not even in the lifespan of our species, but eventually, over the vast timescales of cosmic evolution. Other technological civilizations may emerge on worlds where life already exists. Still, others may develop on planets or moons, yet to form around stars, not yet born. The silence of the present may be merely the prelude to a future rich with diverse consciousness and intelligence. In that future chorus, our voice may remain distinctive, not because we were objectively special or central, but simply because we were among the first to sing. Like the earliest artists who painted on cave walls, or the first storytellers who shaped narrative traditions that would last for millennia, we may be remembered not for our sophistication, but for our pioneering role, for having taken the first tentative steps on a journey that others would continue across cosmic time. As we look up at the silent stars from our small blue world, we might imagine those who will someday look up at the same stars from worlds we will never know. Perhaps they will wonder, as we do, whether they are alone. Perhaps they will search, as we have, for evidence of others who have walked the path from chemistry to consciousness. Perhaps they will find the traces we have left, the signals we have sent, the artifacts we or our descendants have created. Or perhaps the silence will continue, the great filters proving too formidable for most life-bearing worlds to navigate successfully. Perhaps we will remain rare pioneers in a largely unconscious cosmos, consciousness and technology remaining precious islands in a vast sea of unconscious matter and energy. Even then, our existence would represent something remarkable, a demonstration that the universe can come to know itself, that matter and energy can organize into forms capable of contemplating their own existence and wondering about their purpose and future. Whether we are the first notes in a gradually swelling cosmic chorus or rare sparks in an otherwise dark expanse, our existence matters. Not because we are central to some cosmic plan or inherently more important than other configurations of matter and energy, but because we represent something genuinely new in the history of our corner of the universe, the emergence of consciousness and purpose in a cosmos that previously contained neither. As our exploration concludes, we return to the question that began our journey. Are we the first civilization the universe has ever created? We cannot answer with certainty, but we can say this. The evidence suggests we may indeed be among the earliest technological civilizations in our galaxy, or beyond, rare pioneers at the dawn of cosmic intelligence. If so, our existence represents not an anomaly to be explained, but a beginning to be embraced. The first stirrings of a universe, gradually waking up to itself. The silence we observe may be not a puzzle to be solved, but a canvas awaiting the contributions of consciousness and civilization. The emptiness between the stars may be not the absence of what should be there, but the presence of possibility. The open space into which intelligence is just beginning to expand. The quiet we perceive may be not the stillness after a cosmic drama has played out, but the anticipatory silence before it truly begins. Perhaps we are alone now, but not forever. The stars may still be waiting for others to awaken, for more voices to join what will eventually become a vast cosmic chorus. Until then, we light the sky alone, first among the silent stars, early risers in a universe still dreaming of what it might become.